Good afternoon, everybody. I'm Jeff Gerard, the president and founder of the Concrete Countertop Institute and the instructor of our hands-on classes. I'm pleased to be here today to present the Admixtures online training session. This seminar builds on the 18-minute How Concrete Works seminar that explains the primary ingredients of aggregate, cement, and water, the basic main components of concrete. This seminar today goes in depth on all the secondary ingredients such as pozzolans, fibers, and other admixtures. It's these secondary ingredients that allow us as concrete countertop makers to transform ordinary concrete into extraordinary concrete. I recommend that you watch both of these seminars. Obviously, watch the How Concrete Works after you listen to this seminar today. And you can always go back and watch them at your leisure, because this recording, once we're done processing it, will be available at www.concretecountertopinstitute.com/mix-design, which is shown at the bottom of the screen. This seminar is going to give you insight into how admixtures work and when and why to use them. My goal for you is to give you the background understanding to make better choices and improve whatever mix you use. I also have actual from-scratch mix designs as part of another course, the electronic self-study course called Precast Mix Design 101, that includes from-scratch mix designs and an easy-to-use mix calculator for two of my precast concrete countertop mixes that achieve compressive strengths of over 4,000 psi or around 27 MPa in one day. I have many students who live in the metric world, and I'm fluent in both English and metric. So I'll try to present both units because I know the audience today is a global audience. At the end of this course, or at the end of this seminar, I should say, Lane's going to tell you about a sale on this self-study course that I just mentioned. It's a holiday sale, and since it's so timely and relevant for the seminar that you're listening to right now, we thought we'd present it to you and make this offer for you. We'll get it more into detail about this at the end of the seminar, but I just want you to keep in mind that we do have further learning resources available to you. That's the Concrete Countertop Institute's mission, is to provide you, our customers, and our industry with the most relevant and useful information and topics available. With that, let's begin. So the topic today is concrete admixtures, and essentially these are ingredients that modify the cementitious binder. And I have the latest edition of the Portland Cement Association's Design and Control of Concrete Mixtures, and their Chapter 7 on chemical admixtures for concrete lists the 4 major reasons for using chemical admixtures in concrete. And I will quote, "To achieve certain properties in concrete more effectively and efficiently than by other means. To maintain the quality of concrete during the stages of mixing, transporting, placing, finishing, and curing, especially in adverse weather conditions or intricate placements. To overcome certain emergencies during concreting operations. And finally, economy." So those 4 reasons are primarily focused on conventional concrete work, concrete projects. You're pouring a bridge foundation, you're pouring foundation, that sort of thing. Concrete countertop projects are much smaller, a lot more controlled, and we do share a lot of the concerns and the same considerations that conventional construction concrete has. On the other hand, some of the things that are important to us are not shared by the conventional concrete world. For instance, if you're pouring a bridge deck or a parking garage, the client isn't really concerned with minor little hairline cracks in the surfaces or subtle shade differences that might be apparent at arm's length, whereas our customers are. And so the things that are important to us really become magnified because of the types of projects we're working on. And this whole suite of admixtures that I'm going to be talking about are ways that we can manipulate our concrete to better achieve higher strengths, better surface quality, more consistent appearance, quicker turnaround, et cetera, et cetera. So all these admixtures are used to make not only our concrete better, but to make our businesses more efficient. I'm getting feedback. Okay, so why do we use admixtures? I already list some of the four that are in the design and control of concrete mixtures, but for us, some of the major reasons are listed here. For instance, we use pigments to change the color of the concrete. We want to use pozzolans to increase our strength. We use accelerators and retarders to change the set time, et cetera, et cetera. So each one of these needs has an associated admixture that becomes an important tool. It's kind of like having, you want to fix your car, you need a whole bunch of different kinds of tools. You need socket wrenches and screwdrivers and spanners and things like that. And the more you have and the more you're familiar with them, the better you can do whatever you're trying to do. So, as mentioned before, our primary ingredients are, our aggregates, our Portland cement, our water. These are the bones of the concrete. These are the ingredients that I'm not going to cover and touch on now. I will mention a little bit on the importance of the role of water, but with regards to mix designs of grading aggregates and sand and cement and that sort of thing, that's a totally different topic. What we're going to focus on are the secondary ingredients, and these are and I had mentioned before, pozzolans, mineral admixtures, chemical admixtures, of which there are many, many different ones. And I'm going to include fibers, although fibers are technically not an admixture. They are things we add to our concrete, and they do improve the properties of the concrete. So it's an important consideration for us, so I'm going to include it in this topic, even though technically they're not admixtures. Chemical admixtures and physical admixtures like pozzolans modify only the cement paste, and the cement paste is your Portland cement or whatever cement you're using, your water. It's not the aggregates, it's not your gravel, it's not your sand, and as I mentioned before, the fibers, technically it's not the fibers. And the easiest way to think about that is when you add pigments to your concrete, what you're really doing is pigmenting the cement paste. The rocks don't change color, the sand doesn't change color. So that's an easy way to wrap your head around what is an admixture and what isn't. Most admixtures are added to influence the fresh properties of the concrete while it's still workable, but many are also added to influence the hardened characteristics, mostly your pozzolans and perhaps fibers and some polymers too. These are ingredients that are added to the mix. They're generally not replacing part of your ingredients, although pozzolans are used as a cement replacement. Again, they are a little bit of an exception. They're partially considered cementitious in terms of the long-term characteristics of the concrete. So there are differences. There are exceptions to everything. It's kind of like the English language. There are no clear, simple rules. And what I'm going to try to do is make it easier for you to wrap your head around those things. Now, I'm kind of speaking there are a lot of people on today, and I'm speaking to a broad audience who maybe maybe you've been using these things for a long time, or maybe you're just getting into it. So I'm kind of taking the approach that, everybody is a blank slate, and you're learning from me. And if you have different experiences, you're certainly welcome to share those with me. But do keep in mind that there are many, many different kinds of admixtures, and people use them for different reasons. Finally, all admixtures are dosed proportionally by weight to the total dry weight of the binder. And I've given this example of if I had a 2% dose of, say, a pigment, let's say, that would mean I would add 2 kilograms of that pigment to a concrete mix design that had 100 kilograms of dry binder, and that dry binder might be cement and pozzolan. Now, fibers, again, are we'll call it the zebra at the rodeo. They're totally different. They're outside. They're not dosed this way. It's called volume fraction, and when I touch on fibers later on, you'll see how fibers are dosed. So they are they're handled differently, and in some ways they don't make any sense, but that's how it's done. When you're making concrete, and let's be very broad-minded and say whether you're making a patio, whether you're making a bridge deck, whether you're making a concrete countertop or a fireplace around or whatever, you can use admixtures to change and to tweak and to modify your mix designs. And they're used in a very similar way to the way spices are used in cooking, to enhance, to modify, to change, to give it character, so to speak. And you could cook without using spices at all. Your food might be rather bland, but it would still be edible and still be nutritious and all that. Likewise, you can make concrete without admixtures, and certainly people have been doing that for a long time. But there are characteristics of concrete that are difficult to achieve without using admixtures, and the most popular and relevant and obvious one is you cannot achieve a very high fluidity concrete that is a more conventional concrete mix design and still have very high strength without using, in this case, a super plasticizer. If you just had your ordinary sand, rock, cement, and water, the only way to make a very fluid mix design is to add too much water. And by adding too much water, you sacrifice strength and you change many of the beneficial properties of the concrete and degrade them simply in the attempt to add workability. Well, I'm getting ahead of myself here, but here an admixture can be used to enhance the workability of the concrete without sacrificing strength. Likewise, we can change the flavor of food with spices, and by using different spices, we can change the style of the food from, say, spicy southwestern to some other Italian, just by using different spices in the same basic ingredients. So let's say it's chicken. It's a very rough analogy, but if you think of your admixtures as spices that you use as an integral part of the recipe, or as ways to just tweak and modify your mix. A good example would be to just using a little bit of super plasticizer in your mix, kind of like the way you might put salt and pepper on your scrambled eggs in the morning. You may not know exactly how much you need until you start tasting it, which basically means you can't put the salt and pepper in the eggs up front because you don't know exactly how much you're going to need, depending on who's eating it, if you're making it for somebody else. Some mix designs have, say, super plasticizers as part of the formula up front, whereas other mix designs add it at the tail end after the concrete's made, just to tweak and modify and shift the consistency of the mix in a subtle way. So you can use them both ways. So our admixtures are our concrete spices, and different mix designs and different consistencies and different casting methods may dictate one admixture over another, a water reducer versus a super plasticizer. Different mix designs use different admixtures. If I'm pouring a driveway, and that driveway is on a hill, and I want to just add a little bit of slump to my mix and still make a good mix, I'm probably going to be using a low or mid-range water reducer. On the other hand, if I'm pouring a very intricate wall that has undercuts and details in it and I want a high-quality casting, I'm going to be using a very powerful superplasticizer. Same kind of admixture, but a different chemistry. There are many different brands of the same chemistry. So there might be a Glenium versus an Advocast versus a Ritex versus a Creso versus a Speco versus a Sika brand. They may all share virtually the same chemistry, but you may have a brand that's convenient to you, and it makes sense for you to find brands that you trust, brands that are convenient, cost-effective, and easily obtained. And finally, all the ingredients that go in your concrete, the gradation of your aggregates, the surface roughness, the porosity, the cement chemistry, how fine or how coarse it's blended, what are your pozzolans and how much do you have, et cetera, all influence how the admixtures work. So this is not cut and dried. It's not simple, but I don't want you to be overwhelmed. I think by the time we're done with this, you'll have a much better idea of what to use and when to use them. As I mentioned before, there are lots of different admixture companies, and you may have a master builder's rep or distributor right in your backyard. Well, by all means, talk to them, because all these companies make a wide variety of products that I'm going to cover and more, and they all make very similar products. They're in competition with each other, so don't feel that you have to be tied to one particular brand. Now, I'm going to be mentioning specific products that I have used, that I trust, that many people trust my recommendations with regards to concrete countertops. So don't feel that you have to buy what I say. But given that, if you do use what I say, you are going to be getting the kind of results I expect you to be getting. And that goes a long way to having confidence in your product. So let's first talk about admixtures that change and modify the workability of the concrete, how stiff or how runny, how fluid it is. And these include water reducers, and a subset of water reducers are plasticizers, and viscosity modifiers. And I think these are some of the most important admixtures that you're going to want to have at your disposal. Water reducers are essentially chemicals that you add to the concrete that increase the slump without adding extra water. And I found this funny picture of a can of dehydrated water. So that can makes a gallon of water. How convenient to have that. I have a video I'm going to show you in a little while that is a real-life version of that I like to think of as I'm adding powdered water to the concrete. So you'll see that in a little while. I had mentioned earlier that I'm not going to talk about the primary ingredients of concrete, but water is a very important ingredient in concrete, and it's probably the most abused ingredient. And it's probably also one of the main reasons why these workability admixtures were created, is to eliminate the need to add extra water just to gain workability. Like when I teach my students to make concrete countertops, you never, ever, ever, ever do what's shown in this picture, is just add water arbitrarily by eye and judge the consistency based on some, food-related item like oatmeal or whatever. It's super important not to do that, and I'm going to touch on why. So if you just add water to gain your workability, which is probably the only reason why you would do that, adding water, as you know, it reduces strength. Your concrete becomes more porous. There's more voids. There's more channels in it. Those channels allow the water that's in the concrete to escape much faster, leading to increased shrinkage. Those channels and pores are basically sites for future cracking to occur. Adding water changes the coloration, tends to make it lighter, and if your customers are asking for a particular color and you just make your concrete by eye, you're never going to be able to make the same color twice, and it's much easier to control your color if you control the amount of water. And finally, if you're dealing with outdoor concrete, adding excessive water decreases the freeze-thaw resistance, and there are admixtures to deal with that. I'm going to mention them. So in other words, adding water for workability makes poor quality concrete. And if you ever deal with sidewalks and driveways and things like that, you know that that's a very common occurrence. And just to further illustrate how much strength gain is lost, or how much strength is lost by adding extra water, here's this chart from the Portland Cement Association. So this is a whole bunch of different concrete mixtures surveyed over a 14-year period, probably all across, certainly in the United States or North America. And as you can see, we tend to operate in around the 0.35 water cement range. Sometimes it might be 0.330, might be 0.33, but somewhere in this range. So we're typically in, well, my mix designs are typically way up here. And they're also very fluid. But if you just took an ordinary concrete mix design and added water, and it came out of the truck at a 0.50, which is not that uncommon, and then you added water to add workability, you shift it horizontally, and all of a sudden you're riding that blue line down, and you might lose half your strength. You might lose a quarter of your strength just to gain a short-term workability. And I know you folks who make your own concrete mixes are more concerned with the properties of your concrete, because you're going through the effort and the expense of making your own mixes. But it's certainly something to keep in mind, especially if you're dealing with bad concrete mixes. Water plays an important role. Now, your admixtures do depend on the presence of water, and I'm mentioning water because I just had a student ask me this question. We've been dealing with he's working with local aggregates, and he's having a tough time finding the right balance of coarse and fine aggregates, the right type to source. And he was starting with a very low water cement ratio, and he was having to basically max out his super plasticizer, and he was still not getting good workability. And that's very common. I mean, everybody wants to use, or a lot of people want to use, a very low water cement ratio, but sometimes you just have to bump it up a little bit, maybe go from a 0.31 to a 0.32 or a 0.33, just so that your mix has enough fluidity so that super plasticizer, which I'm going to talk about in a little while, is effective. You have to let off the brakes to go forward in your car. So finally, if you add more water, you're diluting everything, and color is one of the admixtures that gets diluted. So your rich purple color becomes a pale lavender instead. And another element that I wanted to reinforce is, when you make concrete, you have all the ingredients we're putting in, the sand, the rocks, and what's important is the cement particles and our pozzolans are finite particles. It's not a mushy sauce. They're finite particles. And the less water you have, the closer those particles are together. And that means that they can start reacting faster, they can start connecting up faster, there's less space, so there's less excess water, there's less porosity. Likewise, as you add more water, everything gets spread out and diluted, and now instead of being a tight solid, it's more like an open, fragile sponge. And it's that open, fragile sponge that makes weak concrete, that makes porous concrete, that really you can't recover from. And so super plasticizers kind of are a sleight of hand, if you will, that lets us have really good concrete that normally would be almost impossible to work with, but make it have the fluidity that we want. Now, I've been talking about fluidity as if that's the only kind of concrete mix you want to be making. And on the left side of the photo is one of my fluid mixes that's an aggregate-based mix. And you could think of it as the closest thing to a conventional concrete mix design that I use. Very fluid, very pourable. But sometimes you want to make a really stiff mix. Maybe you want it to be stiff because you want to pack it vertically up surfaces, or you want to variegate it or hand press it, or whatever name you want to give that look of your concrete. And stiff mixes, the simplest way to make a stiff mix is just to use less water, but sometimes you want other characteristics. You want it to be sticky, you want it to stay together, you want it to have a clay-like property, and there are some admixtures that can help you with that. So you don't always necessarily want fluid concrete. So this is what I mean by stiff concrete. And this is what I mean by fluid concrete, something that you can pour. Now there's a form of concrete that is kind of encompasses the ideal form of a fluid concrete, and that's self-consolidating concrete. And this was developed first in Japan, and then it's moved all around the world because it's such a great mix design where the concrete has a very high self-flow to it. It spreads on its own under gravity, but what's key is it doesn't change consistency. You don't get segregation. So if you look at this disc of concrete it's called a spread, the aggregate is distributed evenly across it. You don't have bleed water on the edges. And that's one of the hallmarks of self-consolidating concrete, is that it's highly flowable. You don't need to put much energy. You don't have to vibrate it to have it do this. It does it all by gravity. And since we're talking about admixtures and we're going to be covering polycarboxylate superplasticizers, I wanted to mention that there's a misconception that you can take any kind of mix and turn it into a self-consolidating mix simply by adding more polycarboxylate to it. And you can't do that. You can get very fluid concrete that way, but it may not be self-consolidating. And sometimes you don't need it to be. Don't think that you have to be making this. Sometimes just grabbing your casting table and shaking it is all the energy the mix needs to flow. That's not self-consolidating if it takes external energy. So it's nice to have this, but it's not necessary. And to make a true self-consolidating concrete, you really have to look at careful aggregate gradation, microfines, and cement-water balances. It's a fairly complex process, and it's very specific to your ingredients. So I could give somebody a recipe for SCC that I developed for my mix ingredients here in Raleigh, North Carolina. But if you happen to be in Sydney, Australia, your aggregates are different, your cements are different. That same exact recipe may not work. It's very, very carefully tuned to the aggregates. So sometimes trying to get a true SCC is an exercise in frustration, and it's not necessary. One of the key principles that I follow certainly when I teach, but when I make mix designs, is I want to keep my mixes as simple and as straightforward and as versatile and flexible as possible. I don't want to make a mix that uses 3 or 4 different cements and 6 or 7 aggregates that all depend on each other, and they're very specific to what I can get today. And then next year when they change, I have to tweak it and do it all over again. That's a lot of work. And to be honest, it's not necessary. It's just a waste of time. There are a lot of mad scientists in this field that like to tinker and constantly change things. And it's not good business practices because your customers don't care. It doesn't matter. It's philosophically fun, but we're not doing this as a hobby. We're doing this as a business. Now, if you're doing this as a hobby, play away. But if you're doing this as a business, you know what? Make good concrete that is consistent, simple, and dependable. And that's my philosophy, and that's where I'm coming from with admixtures. Is they play an important role, but there are a lot of admixtures that you just don't need. So getting back to our water reducers. Water reducers are a general class of admixtures, and as I mentioned before, they add slump without adding water. So you can take a concrete with a constant water cement ratio, let's say it's a 0.4, and then you add this water reducer to it and it increases slump, it increases workability. There's another way to think about it, is when you're starting with your mix, you can achieve a very high fluidity or very high slump, but instead of having to use a lot of water to get there, you can add this water reducer and then use less water to achieve that high slump. So you're really talking about two different sides of the same coin. We can add workability to an existing mix, or we can develop a mix that uses less water to achieve a given degree of workability. And that degree of workability can be very, very high if we wanted to. So here's this video I'm going to show you. It may look jumpy on the screen. In the recording it's going to be fine. It's only a couple minutes long. This is also on our website. So I just wanted to share it with you, and let's see how it looks. So what I'm starting here with is sand and gravel, and I just added water to it. So it's a really simple mix, and I'm adding Portland cement. So this is a totally traditional concrete mix. There's nothing special in it. The water cement ratio is 0.35, and you can see how dry it is. And I've sped up the video, so it was actually several minutes worth of mixing, so it's well mixed. But that mix just doesn't hold together. Here I'm adding a dry superplasticizer at a moderately low dose, and this plasticizer is developed for bagged products. Now look at the consistency when I pour I haven't added a drop of liquid to it, but now it flows like pancake batter. Its water cement ratio is still 0.35. It's, with a little bit of shaking, it self-levels, bubbles are coming out, and that is what I call, adding powdered water. I'm adding workability. So how does it do that? Where does the moisture come from? If when I mixed the cement and the sand and the water together and it turned into this dry, gravelly mix, where did the moisture come from? Where did all that workability come from? Well, it's important to realize that when you make concrete, you're really putting more water than the concrete needs. There's a certain theoretical amount that the cement needs to hydrate, and then everything beyond that is called water of convenience. Well, what we're trying to do is minimize that water of convenience, and that's where your shrinkage comes from. That's where a lot of problems come from. Well, if you had a very powerful microscope and you could look inside the concrete, I've kind of drawn the schematic that illustrates that. You're looking at individual cement particles floating in water. Now, cement particles are very, very fine. They're roughly 1/10 the diameter of a human hair. They vary in size, just like sand particles vary in size and just like gravel particles vary in size. But they're very, very tiny. And very tiny particles have unique characteristics that are not shared by large particles like sand and gravel. When you get down on the microscopic scale like this, these are 10 micrometer size, you get electrostatic properties. There's static electricity, if you will, becomes a dominant force in the microscopic world of cement particles. And your pigment particles are the similar sizes, and your pozzolans are similar sizes, and things like that. So all these little tiny particles are influenced by the fact that they're in water, and water's a polar molecule, and these individual chunks of cement attract water to them, and they get an electric charge, and they tend to stick together, and they form these clumps. And so on the left side of the screen, I've kind of drawn schematics of these large, spongy, open, almost like bubbles of particles stuck together. And these particles, or these clumps I should say, they can trap mixed water inside them. So you're just like if you used a porous aggregate, you're actually losing mixed water. You have less mixed water available to act as a lubricant. And those big chunks act like rough chunks of gravel. Rough gravel's hard to move around. It doesn't flow easy. If you try to stick your hand in a pile of gravel, there's a lot of friction. Well, these big chunks of cement clumps act like big chunks of gravel, although they're very, very still microscopic. They don't move around each other very well. So you've lost some of your mixed water or trapped it, and these particles are now big and rough and angular, and they don't move around each other. And that's why that mix seemed so dry. That's why that mix was so difficult to work with. You would be so tempted to add water to it. But obviously, just by adding some powder, there was more than enough water in there. And this is sort of the insight. This is the secret of superplasticizers or water reducers in general, is that they free up that trapped water. They break up those cement particles, and now instead of acting like big chunks and clumps, they act more like separate discrete particles that can move around each other. And because they're not trapping water, there's more lubrication. The water is kind of like the grease of your ingredients, and it helps things move around. This is a little bit more technical, where you can see the positive and negative charges of the particles and how water gets stuck in between. The different strengths of water reducers have different degrees of effectiveness. So I'm going to mention low range, mid range, high range, and whatnot. And the stronger the water reducer, the more it helps break these clumps up. And the strongest of the superplasticizers that I'm going to cover, the strongest of the water reducers, which are the strongest of the superplasticizers, are called, the chemistry is called polycarboxylate. And the chemistry behind them is even more complex and more sophisticated, because instead of just acting like a dryer sheet that you throw in your dryer so your socks don't stick together, these actually have polymers that coat the particles and act like a physical barrier that helps separate the particles. It's called steric repulsion. It's pretty cool technology, and that's why SCC, or self-consolidating concrete, uses these polycarboxylates. You can use a lot less water and still get a lot of lubrication, so your particles just slide around each other. Very, very potent, very powerful, very versatile. But not everybody needs that. So if you're going to be doing flat work, all you want to do is add a little bit of slump. So you order the truck with a 3-inch slump, so you know you have good concrete that doesn't have too much excess water in it. But you want to be able to spread it and maybe add 2 or 3 or 4 or 5 inches of slump to it. So you would add a lower mid-range water reducer. These don't last a long time. They're just there so that you can spread the concrete around. They don't affect your troweling. They don't make the concrete super sticky. And they're perfect for that application. Likewise, if I was going to cast some sort of precast shape, a column, a wall, a concrete countertop, I want to use something a lot more powerful, because I'm not spreading around. I'm not going to be troweling it. So I'm going to be using a high-range water reducer. Well, high-range water reducers are there to take an existing mix and add a lot of slump to it. I can add 8 or 9 or 10 inches of slump to concrete by using a high-range water reducer. Now, if I take the same exact high-range water reducer and I use it in my mix to use less water instead, it's called a superplasticizer. So they're the same thing, they're just called different things for different when you use them in a different way. So I'm going to be focusing on superplasticizers. They're the potent end of the spectrum of water reducers. Low range, very weak. You might add a couple inches of slump. Mid range is 3 to 5 inches of slump. Translate that 75 to 125 millimeters of slump, let's say. And that's just a rough range. You could probably get it a little bit more. But your superplasticizers, that's where you're really, 6, 8, 9 inches of slump. So 150 to 200 millimeters of slump. A lot, right? Okay. Primarily they're used for precast work because of that high slump, but they certainly can be used for flat work and other field casting works. Generally, we're going to be using them to make very workable concrete that is formulated with a low water cement ratio. And by low, I mean probably below 0.4. Typically, we're not going to be troweling it because we're precasting it, but that doesn't mean it's not possible. It just usually isn't done when you're precasting something. And because we don't have to use so much water to get the workability, we don't get lots of bleed water because there isn't a lot of excess water to make bleed water. So you will find superplasticizers advertised as helping to reduce bleed water. Well, that's why, because there isn't, you don't need it as much water in there in the first place, and if you don't have it in there, you're not going to get it later on. Some popular brands, at least here in the U.S., are of superplasticizers, and these tend to be considered high range. There's one company is called Fritz Pack, and they have a whole suite of products called supersizers. They have a supersizer 1 and a 3 and a 5 and a 7, and the higher the number, the stronger they are. And then there's a BASF product called Melmet F10. It's been around since the 60s. I used it for many, many years. It's a very linear, very predictable powdered superplasticizer. And these types of supersizer 5 or 7 or Melmet F10 or many of the other superplasticizers or high-range water reducers that are on the market, there are probably 10 times more brands that are available that I didn't even mention than the 2 I've mentioned. Excellent when you're trying to just add workability to your concrete or make it sort of flowable. You're not going to make SCC out of these things. You're not going to make super pourable concrete with these. You have to use a lot of them. That's not what they're designed for. If you do want to make very fluid concrete, you're going to be using a polycarboxylate, and it's a different kind of chemistry. So the naphthalene-based and the melamine-based superplasticizers that are, your high ranges, they're going to give you very good workability. But polycarboxylates they're like the drag racers of the sports car world. They do one thing, and their job is to make very fluid concrete. Question, do I have any reservations with regards to Euclid products? Absolutely not. Euclid's a very good company. As I mentioned before, there are many, many different companies on the market that all make very similar products. And if you have a particular company in mind, you're really best, and you want to use one particular company because it's convenient to you or you have an existing relationship with them, by all means talk to them about the products. There are very few companies that make bad products. There are a lot of companies or a lot of products from different companies that all do the same thing, that if you put them side by side and blindfold you, you probably wouldn't be able to tell them apart. Okay, so getting back to the polycarboxylates, I've used these in my mixes for a long time. I do not use these when I'm trying to make a very stiff mix. That's where the Melmet F10 or the Melmet Supersizer 5 or 7 might come in. If I'm making my wet cast mix or making GFRC, I use polycarboxylate, and this particular brand, Ritex, that's been on the market for a number of years now. It's a very predictable, very versatile product that's not very specific to the cements used. Some admixtures are very tuned to a particular region of cement. If you ever go to, say, a Master Builder's website or a Grace website or a Seeker website or a Euclid website, you might see in their high-range water reducers, they have 5 or 6 or 7 different versions that all are described practically the same. And it's kind of, why do they do that? Well, the reason is their main customers are the large regional batch plants that produce cement. So they have their products tuned to a region's cement. So if you happen to be near a cement source that's made, say, in eastern Canada, then there's a particular company's product that is tuned, that works best for that region's cement, versus cement made in Mexico versus cement made in the East Coast of the United States or the Northeast or wherever. That doesn't mean the other versions won't work. It's just that one is going to work better for a certain type of region. These subtleties are not that important to us. A couple questions. Do you know if Optimum 380 is a super polycarboxylate? Yes, it is. Yes, it is. Have you used Trinic Mix? No, I have not. I've been using this for a lot longer than those existed, and I'm very, very happy with it. I have used Optimum. It's virtually identical to Ritex. Looks the same, works the same, smells the same. I do know it's not Ritex, but again, it's one of those different brands that is functionally identical. So if you haven't used super plasticizer before and you're going to be using them in your mix, or if you're just starting out and you're kind of like, oh, where do I start? If you're going to be using one of these, start with a small dose and add known quantities. So you have your mix, you weigh out 50 grams and you just pour a little bit in, see what it does, and then weigh what's left, and that way you know what your dose is. A good tip is to pre-mix your super plasticizer in your mix water before you add the mix water to your ingredients, and then add the mix water to the aggregates, get that well mixed, and then add your cement last. The worst thing to do is to have all the dry ingredients mixed together, add your water, and then add the super plasticizer at the tail end where it's doing the least good. Their job is to help disperse things. That helps mixing. It helps get everything not only blended properly, but the admixture, the super plasticizer, the water reducer, whatever version you're using, starts working faster. So a good dose to start for making precast for a polycarboxylate such as somebody mentioned Optimum 380 or the Ritex is 1/4% or 0.5%. Now what that means is, I'm going to use the metric system just across the board, the units don't matter. So 0.25% means I'm going to add 0.25 kilos of super plasticizer for every 100 kilograms of dry cement added. If you go back to a few slides where I said admixtures are added by weight of dry ingredients, it's, I give the example of 2%. Well, this is 0.25%, 1/4%, or 1/4 of a kilo for every 100 kilos. So a percent is 1 per 100. 1/4% is 1/4 per 100. That's what that means. Finally, other tips. These take some time. Once you put them in, you got to mix your concrete for a couple minutes for them to be fully effective, because those polymeric chains have to start working on the cement particles and disperse them. And if you rush the process too fast, you can end up adding too much polycarboxylate, too much super plasticizer. So you have to be patient with it. They work best with viscosity modifiers, which I'm going to talk about in a second. They are excellent for highly fluid concrete, regardless of the concrete mix design that you're making. They're your best hope of making fluid concrete. However, you have to be careful because it's easy to put too much in and then you get segregation. I'm going to talk about that with the viscosity modifier. Does the amount of super plasticizer you add to your mix affect the color? Yes, it can. If you use too much, you'll tend to get darker concrete, which is actually kind of good, because you want everything to be evenly distributed, evenly wetted out. And if you don't use enough super plasticizer, that doesn't happen. So you don't quite get the color you're expecting. So you'll get the richest, deepest colors by having a powerful super plasticizer when you use enough of it. So viscosity modifiers are a fantastic companion to super plasticizers because they're essentially just the opposite. Super plasticizers make stiff concrete very fluid or runny. I hate to use the term wet because we're not adding extra water. Viscosity modifiers do just the opposite. They make very runny concrete a little bit stiffer. And their job is to help stabilize the viscosity of the paste. This is a picture of SCC, and this is one of the characteristics of what makes SCC self-consolidating, is that that's the edge of an almost 24-inch or 600 millimeter diameter circle of concrete, a big patty that's self-spread on its own. And the consistency of the edge of that concrete patty is the same as it is toward the center. Very, very important. And that's what I mean by stabilization. Symptoms of segregation. Very, very common. I see this a lot with people just starting to get used using the very powerful super plasticizers, or just any plasticizer when they use way too much, but especially the polycarboxylates is they'll put it in their mix, and as it's in the mixer, it's splashing. The concrete's just flowing around. It's gorgeous. It's wonderful. And they dump it in their mix, in their bucket, their dispense. Maybe it's a wheelbarrow, maybe it's a mortar pan or something like that. And they start scooping it into their forms, and very quickly, all of a sudden, they think, oh, it's setting up on me. Well, what's really happening is you're getting segregation because they used too much super plasticizer and they didn't use a viscosity modifier. Segregation was when what it is all the rocks and sand sink to the bottom, and that squeezes out the cement paste. And that cement paste looks like pigmented bleed water. So on the photo on the left, this is actually done on purpose to illustrate this. This is like a charcoal gray concrete that we made in class, and we purposefully put too much super plasticizer in. And what you're seeing is the cement cream. That's the binder. That's a very low water cement ratio cement cream, but it's being squeezed out and forms an excess scum layer of sorts on top. And when that cures, first of all, it takes a little longer to cure because the polycarboxylates can, when they're used in very high doses, they can actually slow down. They can act as a slight retarder. But that scum layer has no aggregate in it. There's not even any sand in it, and that can shrink a lot, and you can get a lot of cracks and crazing in that thin layer. Now, it's only on the backside, and it's easy to grind off. But if you have far too much of that, you can actually build up a scum layer that might be, 1/4 to 3/8 of an inch thick, or 6 to 10 millimeters deep, and that's just a layer that's very poor concrete. So you don't want segregation. This is another photo of self-consolidated concrete that's made improperly. So this may be just a conventional mix on the left that had polycarboxylate added to it. And you can see the cement paste, that's your cement, and in this case just cement and water, just leaking out like paint, like latex paint. And then you're left with a pile of wet rocks. Whereas on the right, that's what it should look like, where it's called it's one of the tests to ensure SCC can flow through rebar obstruction, so it's a standardized ring. And again, you can see the edges look the same as the middle. So on the left, that's extreme segregation. That's terrible, terrible concrete. But you could, by just if the rocks and the sand and all that were correct, you could just add a viscosity modifier and go from what's on the left to the right. Odds are that's not what's happening, but it's potentially possible. So a very common and readily available and economical viscosity modifier is, again, a Fritzpack product called Slump Buster. It's a sodium carbonate, so it's technically not a true viscosity modifier, although it does function very nicely as one. Many of my students can attest to that. You just sprinkle it, they call fairy dust. You just sprinkle it in like a little dash into your mix. It's not dosed. You just add it by eye at the tail end. And a tiny, tiny bit is very powerful. Now, sodium carbonate, when it's added to concrete in larger doses, can act as a set accelerator, and in large dose can actually start to reduce your strength. But we never ever use it nearly to that degree. We're using, fractions of a percent, hundredths of a percent. So the amount we add is inconsequential. Now, there are commercial viscosity modifiers. BAS has one called Starvis. Pretty much every admixture manufacturer has one. Sometimes they're called rheology modifiers. And these tend to be more complex polymers that are more potent, and they have less effective on the setting time or the strength. But you typically can't get those in reasonable quantities. You might have to buy 20 liters of them or even more. Whereas the Fritz pack you can buy in 8-ounce bags, so that's roughly 225 grams. So it's a much more convenient packaging, and there's a lot more distributors. So I've been using that for a long time, and it's a go-to. So if you're going to have a polycarboxylate, you better have a viscosity modifier because they work together. So here's the effect of a polycarboxylate. Now these are different mix designs, but they were both very flowable. So the highly flowable concrete's on the left, and then what you're actually seeing is a GFRC mist coat that normally is the consistency of like a very runny milkshake that has had a lot of viscosity modifier added to it, and now we have a perfect clay-like mix that can be hand-packed. And we didn't have to add a lot to it. So it can become a versatile tool. If you want to make a variegated face coat out of GFRC, you can just use less water and a little bit of viscosity modifier, and bam, you've got a nice clay-like concrete to work with. The next series of admixtures that I'm going to talk about are used to change the strength of the concrete and the setting time of the concrete. So some of these affect both the fresh and hard properties, and some only affect the fresh properties, or we use them only for the fresh properties, even though they can have influence on the hardened properties as well. So I'm going to start with accelerators, and generally they're useful in cold weather. In the winter, when your shop is cold and you don't want that concrete taking forever to set up, or you want to boost the strength gain of your concrete. Generally, the way they work is they increase the reaction rate of the tricalcium silicate portion of your concrete. When you have a Portland cement and you add water to it, you start a chain reaction of chemical reactions. And two of the byproducts of that reaction that are beneficial to us are the generation of calcium trisilicate, which is where your early strength comes from. That generally happens in the first, so let's say, and let's be really generous, 1 to 3 days. And your long-term strength comes from your calcium disilicates. Those are that's where your long-term strength comes from. Now, accelerators tend to, like I said, affect the C3S. That's the shorthand, the shorthand we use to denote the portion of the early strength portion. When you change the early strength, you can start stripping your concrete faster. You can start working on it faster. That may or may not affect your long-term strength because they're somewhat unrelated. Once one's done, it might take, if your early strength is generated in the first day or to 3 days, your long-term strength may not even start to begin. You may not even begin to start generating significant amounts of the calcium disilicates for a week, maybe 10 days. So there's a period of time where one tapers off and one begins. And that's why if you've ever seen the strength curve, you get most of your strength in the first week. You get about half your concrete strength in the first week, and then it tapers off, and you gain most of the rest of the strength in the last month, the last 3 weeks after the first week. And that's an indication of where your early strength has a bigger effect on the strength gain, the rate of strength gain. And when we're in production, everything is about early strength gain. Because I'll be honest with you, there isn't a client out there nowadays that is going to wait 28 days for their customer for their concrete countertops or whatever you're making. We want to cast them, we want to strip them, we want to get them out the door as fast as possible. So accelerators in general, and I don't necessarily mean chemical accelerators because I'm going to also talk about thermal accelerators, are a way to boost your production rate, to boost your production efficiency by speeding up your early strength gain. What we don't want to do is sacrifice long-term strength, though. That's something nobody wants to do. Now, in the construction world, calcium chloride is a very common, popular, and very inexpensive accelerator. But there's a big problem with it, although it can lead to corrosion reinforcing steel, it's not really important for us. What is important for us is it can discolor and cause mottling, especially in colored concrete. And that is not something we want. And that may be why you think there's a color change in the long term. It may be from calcium chloride. I've used non-calcium chloride, specifically a calcium diformate. Fritzpack's NCA is one brand that is a calcium diformate that does not affect the color at all. It's more expensive and is not as potent, and it doesn't work as fast, but it is the preferred accelerator if you're going to use a chemical accelerator. And what a lot of folks do is when they're grouting their concrete to fill in the pinholes, they put an accelerator in their grout so it hardens faster. There is another way to accelerate your Portland cement, and that is to add CSA, or calcium sulfoaluminate clinker. And this does accelerate the strength gain, it accelerates setting. It can make the concrete set very, very fast, minutes. These clinker additives are designed to work with Portland cement. They're not cements on their own. They have to be used with Portland cement. And when you have a concrete mix that uses Portland cement, you still have calcium hydroxide being generated. So you still need to then use pozzolans, which I haven't talked about yet, but I'm going to jump ahead and say you need to use pozzolans. So these type of accelerators, these CSA additives, force you to have now 3 cementitious ingredients because they're not cements on their own. Typically, they're used as 15 to 30% of cement replacements. The more you use, the faster it is. So the only real clinker that's on the market nowadays is this stuff from a company called Bootsy Unisem. They used to make a product called Quicks, and it doesn't seem to be available anymore. If it is, this is basically the same thing. According to their website, this is not a CSA cement. I am going to talk about a pure CSA cement in a second, but this is not a CSA cement. This from their website says it's made to be used with Portland cement. So this is an additive that you blend into your concrete, making your concrete more complicated and complex. The more you use, you're going to get higher early strengths. So you might get 3,000 to 4,000 psi in one day, maybe more, but you're also going to reduce your set time. And to control that, you have to use ice and citric acid. But because citric acid is such a potent retarder for the Portland cement and a fairly moderate retarder for CSA cements, you have to be very careful on how much you use. When people first started using these things, maybe I'm going to say 6-7 years ago, there was lots of problems with people putting too much citric acid in because they wanted the normal work time you would have with Portland cement, a good 45 minutes to an hour. Well, if you use enough citric acid to do that, you've basically turned your concrete into mush, and you're never going to get the good kind of strengths you want. So it's very complicated to manage these things. It's doable, but you have to be really careful about it. I don't recommend these things. You're making your concrete much more complicated, and it's harder to control. You're still not making pure white concrete. And if you want something that gets fast, if you want it to be hard quickly, just use this stuff. So there's another company in the U.S. called Rapid Set that makes CSA-based cement and concrete mixes. Rapid Set makes a pure CSA cement. It's not an additive. You can use it all by itself. I've made lots of concrete with it. I've made stiff hand pack, I've made wet cast, I've made GFRC with it. Use it instead of Portland cement. You do not need pozzolans. They don't work because CSA cements don't generate calcium hydroxide. With Rapid Set, the cement you get 28-day strengths in 24 hours, and that strength might be around 10,000 psi or 70 MPa, which is realistically achievable in 24 to 30 hours. that means that you can cast a piece and strip it. I physically cast a tile and started grinding to expose the glass and started polishing it within 2 hours of casting. So these are real numbers, and it simplifies things a great deal. Again, my philosophy of keep it simple, keep it less complicated. This is what I use instead. And it uses citric acid as a set retarder. So although it can react very, very quickly, I could give anybody who uses this stuff an hour's worth of work time. So it's very easy to manage. So I had mentioned that I was going to talk about a different kind of accelerator other than chemical. And the most common, perhaps the oldest, is heat. Commercial precast, they use steam curing. When you warm up concrete, and it's not just the surface, but you're warming the full body of the concrete, the reaction rates speed up. So a good rule of thumb is concrete's going to gain strength. It's going to the whole hydration process is going to react about twice as fast at 90 degrees Fahrenheit than it is at 70 degrees Fahrenheit. And there's the metric equivalent for you. So when it's hotter, things happen faster. It's like the clock speeds up. You're getting free time, and that's why a lot of precast concrete is steam cured, because they raise the heat in a gentle, controlled fashion to a moderate temperature, perhaps 120 degrees Fahrenheit, maybe a little bit more, and hold it there for 8-12 hours or so. And it's kind of like the concrete sits in the forms for 2 to 3 times that length of time. Maybe it's like 12 hours at 50 degrees centigrade is kind of like 36 hours at 20 degrees Fahrenheit. So it's if you can give your concrete heat, you can really buy yourself some time. And always remember, concrete generates its own heat. So if you just put insulation on it, you can trap the heat it makes. Now, in the winter here, it's winter here in the northern hemisphere, and your shop is probably cold, your mixed ingredients are cold, and cold concrete doesn't react very fast. And I'm going to mention that when I talk about retarders next. Well, to kind of kickstart things, use hot water. So use hot water as your mixed water. That's going to warm up all your ingredients from maybe being 50 degrees or 10 degrees C up to around that 20 degrees C, that 68, 70 degrees Fahrenheit. It's going to help get things going so that it can generate enough heat in a meaningful amount of time. Question, when using CSA cement, do you still require a polymer? Yes, and when I'm going to talk about polymers, you'll understand why. CSA is just another form of cement, whereas GFRC is a concrete. Can I overheat concrete? Yes. You never want to get above 140 Fahrenheit. Don't know what that is in centigrade off the top of my head, but it's pretty hot. And you never want to get it hot fast. Commercial steam curing ramps up at a specific rate. You can Google that. And they hold it at a given temperature, and then they let it cool down. If you heat up the concrete really fast and then cool it off really fast, you could shock it and actually cause cracks. So it has to be a gentle process that's, you go from room temperature up to that full temperature over maybe 8 hours or so. Gentle warming. And when you do warm cure your concrete, you're only gaining strength at that temperature while the concrete's warm. Once it cools off, it's going to slow back down. It's kind of like driving your car. You only go fast when you push the accelerator. And there are no downhills to coast, so to speak. Now, opposite of an accelerator on your car are your brakes. So retarders are ways to slow down your concrete. And I think the best conditions to make concrete in, this is my preferred way, I like the environment I'm in to be hot, and I want to make my concrete cold. The opposite of having a cold environment and having to make my concrete hot, that takes a lot of effort. But it's very easy, and in my opinion, much more pleasant to be in a warm environment, but to work with cold concrete, because cold concrete reacts slower, just the opposite of hot concrete. Well, we can also use I'm going to talk about chemical retarders first, and then I'll talk about chilling the concrete. So again, when you slow down the reactions, you slow down the early strength gain, so you're going to lose some early strength when you retard to concrete. But because the crisp hydration rate occurs slower, you actually increase your long-term strength. And that with Portland cement, that may not be terribly significant, maybe 5%, 10%. That's a fairly insignificant amount. With CSA cements, when you retard them a lot, when you use a full dose of retarder, you can actually gain up to 30% more strength than if you didn't use retarders at all. So it's a huge, huge gain. 10,000 to 13,000 psi, and guess what? I get all the work time I want. Wow, what a bonus. Very easy to do and very inexpensive. There are lots of different commercial retarders on the market, and different companies have different chemistries. They blend them differently. They have all different names. I don't have any one in particular that I could recommend over another. In the past, I've just used table sugar. It is a recognized retarder. It's very unpredictable, though, so you have to be extremely careful about how you use it. Typical dose is 0.1%. The maximum dose I would ever want to use is 0.15%. And if you use too much, and that too much could be 0.25% or more, you can get some funky results where you get a flash set up front and then this concrete never gains any strength. That's called killing the concrete. So sugar is a very powerful retarder, and it works in weird ways. But at least if you use pure cane sugar, certainly don't ever use anything like a sugar substitute, you can get a reasonable amount. Now, many, many years ago, it was about 12 years ago, I was working on a project, and I had a fair amount of concrete to cast. And this is when I only had one employee, and he was out sick for the day, and I had to cast. So I'm kind of literally short-handed. And it was a little warm, and I was really concerned with my ability to cast and place all the concrete by myself. And that's always something that everybody who begins with faces. I knew that sugar was an acceptable retarder, but in my shop I didn't have any. I did have a refrigerator full of soda, and by back calculating a 0.15% dose for my concrete mixes, I needed 38 grams of sugar to add to my concrete to give me probably a good 20-30 minutes of extra work time, which was all the work time I needed. And the only sugar I had in my shop was a can of Sprite. Sprite is a lemon lime soda here in the United States. So I added it to the concrete. It's not certainly not something I recommend. The concrete smelled like Sprite. It was fine. It got strong. It worked, but it worked because I knew that sugar, not high fructose corn syrup, but sugar at the right dose would work. Okay, what are you using the percentage? What is the measurement? Again, percent means weight of admixture to dry weight of your cementitious. It doesn't matter what the number is. It doesn't matter what your units are. It's always weight of admixture to weight of dry cementitious. Mils are volume. Pounds are weight. Kilos are weight. Grams are weight. So it's not volume, it's weight. Another retarder that's a very powerful retarder, it's also fairly commonly available because it's a generic ingredient in a lot of things. It's citric acid. Most citric acid that you buy on the internet, that's where I get mine, is a food grade citric acid. That doesn't mean anything. I don't care that it is. It's cheap. It's $2 to $3 a pound. I primarily use citric acid when I use CSA cements because it's really hard to work with them when you do not have a retarder. So the dose for CSA cements, the rapid set, is 0.1 to 0.4%. And a rough rule of thumb, at room temperatures, every 0.1% increase gives me about 10 to 15 minutes of extra work time. So at the maximum dose, 0.4%, or thereabouts, I can get up to almost an hour's of work time by using citric acid. Now, if it's really hot out, I'm not going to get the full dose, full hour. I might get half that or a third of that. And I had already mentioned that by using citric acid, because it slows the hydration rate down, it changes the size of the crystals that grow in the concrete. And when you slow down crystal growth, you get smaller crystals. You get better crystal arrangement, and that leads to stronger concrete. And that is borne out by many independent tests of rapid set. One easy way to think about this is if you had you're going to build some furniture and you wanted some really strong wood, you could have wood that comes from old growth wood, where the grain is very small and tight, the growth rings are very small and tight, or fast growth wood where the growth rings are really wide and broad. Old growth wood is much stronger because you have a tighter grain structure. Citric acid is a retarder for Portland cement, but it's very, very powerful, and like sugar, you have to be very careful with it because you can literally have concrete that takes a couple days to set and gain any meaningful strength. So I would suggest you don't go beyond a 0.1% dose of citric acid. There are other ways to slow your Portland cement down in a much more gentle way that doesn't affect your long-term strength, and I'm going to get to that in a minute. So you really only need one retarder, and that's citric acid. But again, you have to use it carefully. The final way of slowing your concrete down is with ice, and use ice as part of your mix water. Now you can also just use cold water, but you can only get your concrete so cold by using cold water. When you use ice as part of your mix water, the melting of the ice can really drop the temperature down to where you could literally add too much ice and you now have ice cubes floating around in your concrete. I hope you all got the visual joke on the screen. So when you use it as part of your mix water, it's added to your ingredients as part of your mix water. So you put it in your bucket, you put your ice in, you add the rest of your mix water, and let's say you needed 3.7 kilos of water. You might start with a certain amount of ice, add that to your bucket, and bring the remaining up to the proper amount of water. The whole point of using ice is your hot ingredients melt it, and if you don't add too much ice, which you should never add too much ice, by the time you're done mixing, all the ice melts. And guess what? Ice floats, so you can always see unmelted ice because it's right at the surface. It's very easy to see. And in the bottom photos on the left is a GFRC mix we're making with ice. It's very, very common and is always done in commercial GFRC to use ice because your concrete is very predictable when it's the same temperature. On the right side, I did a project in the Cayman Islands casting this big bar. It's like 180 square foot bar in one pour to cast in place. And because it's summertime temperatures, it's almost 90 degrees Fahrenheit. To give the work time, I had 500 pounds of ice added to the mix to chill the concrete down to where it wasn't setting so fast. So I didn't use a chemical retarder. I physically made the concrete colder. And when it's hot out and you're working on cold concrete, it's really comfortable. It's really nice. And the great thing about ice is once that the concrete's cold, you get it really cold. It's not dormant, but it's gaining strength slowly. It's setting much slower. You have all the time you need to place it, to finish it, to vibrate it, to do whatever. When you're done, you walk away, it warms up. Now it's at ambient temperature. That ambient temperature is hot, and now your concrete starts setting much faster. And it's setting at a comfortably accelerated rate. So you're kind of getting the best of both worlds, and ice is readily available, and it has no effect on the strength of your concrete. Now, predicting how much ice you need can be very complicated. It's a fairly sophisticated thermodynamic set of calculations. That there are no simple rules of thumb, like, oh, just use 1/3 of your mixed water with ice. Well, it depends on the temperature, ingredients, and whatnot. So I created an ice cooling calculator, and it's part of all my mix designs, my GFRC, my precast mix designs, where you can input your ingredients, the temperature ingredients, and get a very good prediction of the final mix temperature. It's usually good within a couple degrees, which is close enough, so that you're not putting too much ice in. Because the last thing you want to do is add too much ice. You're done mixing, there's still a lot of ice left, and you have to stand around waiting for it to melt. Or, as somebody mentioned, you cast with it, and all of a sudden you have these ice cubes the ice cubes are part of your mix water, so your concrete wouldn't have the right mix water cement ratio in it anyway, so the ice has to melt. It's very important not to use too much ice, but it's easy to not use enough. And because it's part of your mix water, you just can't add ice randomly because you're adding more water. So this calculator is really the only way that you can achieve a target temperature, I like around 50 degrees or 10 degrees C, and not go over your mix. Now, it doesn't matter what cement you're using. If I've found that it's hard to get your concrete much colder than, say, 50 degrees Fahrenheit or 10 degrees C and still have all the ice melt by the time you're done mixing. Let's say I wanted to target 40 degrees Fahrenheit, which is like, what, 8 degrees C or something like that. I gotta stand around and wait for that ice to melt because I've already sucked all the heat out of there's really not enough heat left in the concrete mix to melt all that ice. So there's a point where you're just adding time. It's not helping you. So 50 degrees is really the cold enough. Now, in terms of just taking a CSA-based concrete and casting it in your shop, you could cast it at, say, 32 degrees. I wouldn't necessarily cast it outside when you got to still deal with proper cold weather concreting practices. I'm not talking about casting in extreme temperature conditions. I'm talking about just making it so we have lots of work time. All right, so those are the admixtures that really focus on the work time up front. The strength aspect is mainly done with pozzolans, and these are mineral admixtures, and they're also called supplementary cementitious materials. And there's a common definition that's thrown about. It's in the quotes, and I'm not going to read it because you can read it instead of me saying it. These are mineral admixtures that are put into the concrete, and they can be used in addition to your cement or as partially as to replace some of your cement to make your concrete better. I'm going to explain what they are, how they work, and the differences between them. Some of them are natural materials, some of them are manufactured, some of them are processed waste products where they're more controlled, and some are waste products that are used with virtually no processing at all. And the ones I'm going to touch on are metakaolin, silica fume, fly ash, slag, and vitrified calcium aluminosilicates, or also known as VCAS. And there are similar products like VCAS, but I'm going to focus on VCAS. So this is kind of what they look like. Fly ash tends to be sort of a light grayish brown. I've seen fly ash that's almost pale buff. I've also seen fly ash that's almost black, and the color comes from a lot of the darkness comes from carbon content. Metakaolin is very white. Sometimes it's kind of a creamy pink. After it reacts in the concrete, the color goes away. I've made white concrete with metakaolin that looked kind of pinkish cream, and it looked identical to white cement-based concrete that didn't have any metakaolin in it. So the color of the pozzolana when you're holding it in your hand isn't representative of the color of the pozzolana after it's done reacting. Now, fly ash and silica fume, that dark bluish gray one, those colors are preserved. You still see that. Slag is kind of whitish. VCAS is also whitish. I've seen VCAS be kind of grayish, and there's some other waste recycled glass derived pozzolans that tend to be a little bit of a creamy brown because they have a lot of brown bottles in them. So this is basically how they work. When you have water and you have Portland cement and they react, one of the byproducts I already mentioned, the calcium silicate hydrates, that's a gel, that's a desirable stuff we want. Well, there's a byproduct, it's calcium hydroxide. And calcium hydroxide isn't terrible. It's not great. It weakens the concrete a little bit, but you still can make decent concrete without dealing with it. But about 15 to 20% of your Portland cement eventually turns into calcium hydroxide. Depending on the cement formulation, it could be more, it could be less, but it's about, let's say, a fifth of your cement. That's a lot. Calcium hydroxide is what makes the concrete very alkaline. That's what gives you the cement burns if you get fresh concrete on your hands. If you've ever taken a piece of concrete out of the forms when it's brand new and run your hand over it, sometimes the concrete can feel slippery. It feels very slick. Well, concrete's not slick. It's not slippery. What you're feeling is the calcium hydroxide dissolving the proteins in your skin. So you're actually feeling your skin dissolving from the high alkalinity. Just like if you've ever splashed bleach on your fingers get slippery. That's your skin dissolving. Well, that's how powerful calcium hydroxide is. When we add pozzolans to our concrete, the pozzolans react with the calcium hydroxide. It's called activation, and it's called alkali activation because it needs a very strong alkaline solution to do it. And that alkalinity reacts with the chemistry of the pozzolan to form more of the calcium silicate hydrate gel, which is the desirable glue that holds everything together. So we're making more glue from the waste product is what we're trying to do. We treat pozzolans just like cement, pound for pound or kilo for kilo. Often we use them as a cement replacement, and I'll explain that in a little while, why we do one versus the other. One thing to keep in mind is that pozzolans take time to react, and different pozzolans can react much faster than others. Most of them react quite slowly. And the different chemistries and all give you different reactivities, as well as the temperature you're curing it at and whatnot. To give you, I'm going to jump ahead and give you a rough idea. You don't even start to see any strength gain from VCAS. This is based on my tests done on cylinders for at least a week, maybe more. So most of your strength, well, all of your early strength, and by that I mean 3 to 7 days, comes from the cement portion in your concrete, not from the pozzolans. There are a couple exceptions. I'm going to talk about that as I go on. So here's sort of a flow chart that the source I got this from was talking about using specifically silica fume to make more durable roads or exterior concrete that's subjected to freeze and thaw. But if you look at it in a general sense from pozzolan, this still holds true. When we add pozzolans to our concrete, we consume the calcium hydroxide, so there's less of it. That creates more calcium silicate hydrate gel that gives us higher strength, helps plug the pores. There's less open space. Calcium hydroxide is a big crystal that's very soluble in water. So once it dissolves, it leaves a big void behind, and that mineral salt, if you will, leaches to the surface and forms part of what you see as efflorescence. Well, those pores are plugged, so our concrete has less permeability, and there are fewer open pores to hold water, and that open water, there's less of it, so we have better freeze-thaw resistance. So there's less free water in the concrete to freeze. Water can't get in. There's not that many spaces for it to be in, so we have superior durability concrete. And that's the general sense of this is why, in a single slide, I always use pozzolans in all of my concrete. Pozzolans also, they're physical particles. They're very, very small, and they help to pack as microfiller in between the cement particles and the aggregate. Some of these react to form the gel, and some don't. And so in essence, they're helping to fill in and bridge some of these gaps. So you get a stronger bond between your aggregates and the cement particles and everything else. These are scanning electron microscope photographs of calcium silicate hydrate crystals, and those are those big sort of really sharp, angular looking flat platey things. If you can see my mouse, that's some right there. And this is the outside of a tiny sand grain. This is a pore, an open bubble in the cement paste, and there's some calcium silicate hydrate crystals that have formed. 100 microns, if you could take a human hair and cut it in half, that's the width of a human hair is right there, 100 microns. And then over here we have the big flat platey crystals forming. And these long, slender things that look like fibers are actually edringite crystals that are formed in the concrete. But mostly what we're looking at here is the calcium silicate hydrate crystals. And these form, they like to form on the surface of the aggregates. So they kind of act like bond breakers that prevent the cement paste from bonding really well to your aggregate, so you get weaker concrete. Well, what our pozzolans do is they consume it, they make it go away, they create more gel, and now we get a better bond, and that's where this better strength comes from. I'm not going to read this list. These are the reasons why we use pozzolans. They're all very beneficial. Because a lot of them are recycled, we're actually increasing the green content of our concrete. And that's important to some people. And as we step through the different types, and I have a little chart of typical dosage, you kind of get a sense of what's used when and where. Probably the most common pozzolans used in construction world is fly ash, but it's not used in concrete countertops a lot, and I think you'll understand why as we step through these. So I use these as a cement replacement. Basically, it doesn't affect my paste volume. I have a fixed amount of cement paste, and part of that cement paste is Portland cement and part of it is pozzolan, but the total volume of it is still the same. So it doesn't mess with my colors, doesn't affect my water cement ratio, it doesn't affect my mix design. All the calculations are very simple. The downside is, as I replace more and more of the cement with pozzolans, I take away the cement that provides the early strength. So high cement replacements yield low early strengths because there's not a lot of cement to hold everything together. You can also add them. Typically this is done if you have let's say you have a concrete truck and it's delivered and you want to add pozzolans to it. Well, you can't take cement out because it's already mixed in. You're just adding bags of pozzolans to that mix. Here you're boosting your cement paste volume, and because the pozzolans are counted as part of the cement in the calculations, your water cement's affected. And of course all your admixtures or doses change and all that. So it's not done as an addition because it kind of messes with all the proportions of everything, but it's certainly not a horrible thing to do. It's just a lot harder to deal with on a mathematical basis. And if you add, since you're not changing your cement content, your early strength doesn't change relative to not using pozzolans at all. But if you add too much pozzolan, the unreacted pozzolans, they don't do anything. Pozzolans on their own don't have any strength. They just act like microfine sand, which may or may not be a good thing. It's never bad to have some microfines, but it's sometimes what can happen. Here's the scenario: is you add too much pozzolan because you're boosting your cement paste and you're not changing your water cement ratio. All of a sudden the concrete gets stiff, and the common reaction is to add more water to the mix to boost the paste, get it more workable, and now your strength goes down because you've had to add more water. The proper thing to do would be add more superplasticizer to the mix, but that can be problematic too, just by trying to dose it by eye, as I had mentioned before, with segregation and all that. So in concrete countertops, the two most common pozzolans are VCAS and metakaolin, and VCAS being the vitrified calcium aluminosilicate, and I'll step through what that is. But the reason why these are used is because they're white. There are lots of different pozzolans. Some I'm not mentioning. Rice hull ash, for one. There are a bunch of other ones. They all have different chemistries. And so this little ternary diagram that shows the various major chemical components of the different things, the blue dot is Portland cement. So where the different pozzolans fall on this triangular shaped chart kind of illustrates the components of what the chemical makeup of these. Silica fume, which is a dark gray dot, is almost pure silica. It doesn't have any calcium in it, doesn't have any aluminum in it. Metakaolin doesn't have any calcium in it, but it has roughly equal parts silicon and aluminum in it. And blast furnace slag, the yellow dot, is closest to cement. It almost has no aluminum in it, but it's almost equal parts calcium and silicon. So that's how you read this diagram. I just showed it just for illustration purposes. You don't have to care about any of that stuff. And the PFA means pulverized fly ash. So it's fly ash. Different pozzolans do different things at different rates. That's what all this slide says. So you can't just substitute one for another and get exactly the same results. So let's talk about the individual ones as we go. And this is the most popular one. This is the one that I use a lot. VCAS. It's made. It's a single manufacturer made in Georgia. And what it is it's post-industrial fiberglass waste. It's very finely powdered fiberglass waste. Because they can control the waste stream that they choose, the end product is nearly white. When it's added to concrete, it tends to increase the workability. Therefore, I hate to say that reduces the water demand, because that assumes that you're using water to change your workability, but it's a common way of describing things. In other words, if you use VCAS in your mix, you don't need to use as much super plasticizer to get the kind of workability you want. That would be the better way of describing it. The average particle size is 3 to 8 microns, although just like sand, there's all different size ranges. Typically about as fine or finer than cement. It has good reactivity, which is why it's used. So the reason why it's used is it gives you great workability. It's white, so it doesn't affect your colors. You can make pure white concrete with it. It's a green product. Good reactivity, so we have decent early strength. It tends to be used in a slightly higher dose. I'll talk about the doses in a little bit. Before VCAS came on the market, the pozzolan of choice was metakaolin, and it's still a very, very good pozzolan. It's an engineered pozzolan. They take raw kaolin clay. Most of it's mined also in Georgia, ironically, right next to where VCAS is made. And it's calcined, which means it is heated at a very controlled temperature for a very controlled amount of time, and it chemically changes it. So metakaolin meta is Greek for change, and kaolin is a type of clay. So they change the clay from, you'd never ever put kaolin clay in concrete. It would weaken your concrete. But when you use calcined clay, it's chemically changed, it's now chemically reactive. It gives you a very highly reactive, very small particle pozzolan that can actually give you higher early strengths. You can get higher 3-day strengths using metakaolin than you would if you didn't use pozzolans at all. So this is one of the few pozzolans that actually boosts your early strength. Probably the one reason why it fell out of favor is because it's engineered from raw materials. It's technically not green. Or as green, let's say, although it's a very fuzzy topic I'm not going to jump into. And it tends to make the concrete sticky and reduce your workability, which is actually useful for some things, because it kind of can act like a viscosity modifier in your mix. Prior to metakaolin coming on the market, the only really high-performance pozzolan that was available, and not very readily available, was silica fume. Historically, the only silica fume that was available was the normal stuff that's sort of a dark bluish gray. There's a photo up top of there's a white silica fume and a gray silica fume. And the white silica fume is much more expensive, but equally as effective. Silica fume has been historically used to make ultra-high performance concrete where you're pushing 10, 15, 20,000 psi concrete. Very, very high. It's used in oil rigs and nuclear reactors and stuff like that where you need very, very dense, very strong concrete. Average particle sizes are smoke size, 1/10 of a micron. Very, very small. Fraction of a human hair. You get very high reactivity. But the trade-off is it can make your concrete very sticky if you use it in high quantities. So it's described as having a very high water demand. Again, that very bad habit of using water to change your workability. I've used silica fume in the past. I've blended it. You can blend. The great thing about pozzolans is you can blend them. Now, getting into blending means you're starting to delve into a world of, are you changing things and is it getting any better? One pozzolan is perfectly good. 3 just makes it more complicated. It's not necessarily going to make it better for your customers. There is a brand of pozzolan sold on the market called Altopoz that's a blend of VCAS and metakaolin. Don't know what the proportions are, but that's what it is. You can make your own because that's what the ingredients are. There are blends of silica fume and fly ash and slag and silica fume and fly ash and whatnot. You can go on and drive yourself crazy sourcing and blending all these things till the sun comes down. In the end, what we want is good, strong concrete that we can get out the door quickly. And adding an extra pozzolan doesn't necessarily mean we're going to make extra better concrete. It just means we make more complicated concrete. So I'm going to get off that soapbox and talk about fly ash. It's, again, the most popular and most commonly used pozzolan in the construction world. And that's because fly ash, there's a lot of it, comes from burning coal. And coal is burned for power in a lot of places in the world. And there's a lot of fly ash generated. And unfortunately, most of the fly ash that's generated is still landfilled. The fly ash industry is trying to use as much of it as possible in concrete, and it's a very economical way of making your concrete less expensive. So instead of, let's hypothetically say, I want to make a 4,000 psi mix or 4,500 psi mix, which would be 30 MPa in round numbers, and that's all I need. Okay, so that might be a driveway, that might be a house foundation or something like that. You can order concrete made with 100% Portland cement that does that, and it's going to cost a certain amount. But if you ordered it with fly ash as a substitute for some of your Portland cement, the per volume cost of that concrete is going to be lower. Now the end result, the 28-day strength of that concrete might be the same, but the early strength is going to suffer. Fly ash has a slow reactivity, so you're going to lose early strength. It tend to be used in high substitutions. One of the benefits of using fly ash is because these are small glassy beads, they look like tiny ball bearings. It adds a lot of workability to the concrete. You can make very flowable concrete. The reason why it's not used in concrete countertops is because it's a completely non-refined product. One source might be the color you see in the picture, another source might be black. Next year when you get it might be a different color. So you have no control over your colors or the shade of your colors, and you lose a lot of early strength. The reactivity is very slow. So you might not even start to see a recovered strength for a month or so. Well, that's too long. It's fine for the construction world, but not fine for us. And then another pozzolan that's a pure waste product is called slag. It's technically called ground granulated blast furnace slag, or GGBFS, and it comes from the refining of steel and iron. So when they're melting steel, or they're taking raw iron, they're turning it into steel, they have to control the oxidation of it, and so they melt. They put in limestone, and they put in some other kinds of minerals that act as a flux. So this rock melts on top of the big kettle of molten steel, and not only does it block the oxygen from getting to the steel and causing it to oxidize, but it also acts as a sponge to help suck impurities out of the steel. Well, once they're done cooking the steel and doing whatever they do to the steel to get it the way they want it, changing the chemistry of it, they've got basically man-made lava. It's liquid rock. They have to do something with it. Well, if they just pour it into a big slag heap, it basically forms man-made lava. Well, to get rid of it, since there's a lot of it made, they can spray water through it and turns it into granules. And that chills it really fast, so as the rock cools, or the liquid rock blend that has all the stuff in it, as it cools, it basically changes the chemistry, so it becomes reactive. And it becomes reactive when it's ground up into a fine powder, and it's ground different degrees of fineness, and that's why there's different grades of it. The finer you grind it, the more reactive it is. The chemistry of slag is such that it has a little bit of calcium oxide in it, so it is self-cementing to some degree, and it tends to be used in high replacement doses. It adds workability, which is why it's used. It can improve a lot of properties of concrete, but it's not very reactive as compared to Medical and silica fume. So you have slower set time, slower strength gains up front. Again, in the construction world, it doesn't matter, but for us it does matter. Perhaps one of the biggest reasons why I'm not a big fan of it is there's a definite greening effect. Slag tends to have a lot of iron and manganese sulfides in it, and how much depends on the kind of steel and what they're making. Again, because it's just a sponge to suck all the impurities out of the steel. Well, we're using that sponge that has all those impurities in it as our pozzolan. Who knows what it is, and who knows what the steel was when we get it. So its composition can change from source to source and from time to time. And these sulfides, when they react with water and the alkalinity of the concrete, they can turn green. And I've seen slag cement look, like seaweed green. It can look kind of nasty, and it takes time and air and oxidation for that greening to go away. Sometimes it looks bluish. That might take a few days. I've seen concrete where it doesn't go away. Some concrete, countertop concrete made with it, I've seen it go away too. But it's a possibility. It's a real possibility. And there's actually an association, the Slag Cement Association, that talks about the greening effect and how over time it will disappear, but when you strip the forms, you're going to see this green blotchiness. Something to keep in mind. So when you're adding these pozzolans to your mix, when you blend them into your mix and formulate your mix, they're going to have different effects. And so this is from the Portland Cement Association. It certainly doesn't cover all the pozzolans I use, but it's not, VCAS is not on here, but you get a general sense of what's going on. So the water requirements for flash and slag are lower, silica fume's much higher. I would say that if you add VCAS, your workability is going to increase just like slag and flash. Plastic shrinkage, cracking, all these things, set time and all that, are affected differently. Again, the way pozzolans work is they need calcium hydroxide to be activated. They don't do anything on their own. Calcium hydroxide is generated as the cement hydrates. That takes time. So nothing happens instantly. And the more pozzolan that replaces cement, the less cement there is to generate calcium hydroxide. And it takes a certain concentration of calcium hydroxide to kickstart that pozzolan to turn into the calcium silicate hydrate gel. So if you have a very slow reacting pozzolan that you use a lot of as a replacement, you only have a little bit of cement, so your early strength is going to be lower because you only have a little bit of cement to provide that strength. And then it takes a long time for that strength to build up to where it exceeds the strength of the concrete that it would have had if it was only made with cement. So that's why I don't like to use slow reacting pozzolans, because they have a big negative effect on your early strength, and that's what's everything, to me at least. And here's some typical doses. Now, different people use different doses, and you could do whatever you want, but these are the typical ranges. For VCAS, in my precast mix, I use 15%. I've gone down to 10%. I don't like to go up above 15% because I'm starting to lose early strength. In GFRC, I use 20% replacement because I have all those fibers to help boost my green strength of the concrete. I don't have that in the precast. Metakiln, because it's much more reactive, 10 to 15%. Typically, I've done 10%. Silica fume, 5 to 10%. 10% is a lot. 10% is a lot. Typically, it's 5 to maybe 7%. And then I don't have that much experience with slag, but some folks have gone less, some folks have gone more, but 30 to 45% is roughly what the construction industry uses as a replacement. I've seen mix designs that use 100% slag. I've seen mix designs that use, say, 75 to 80% slag. But that's the kind of concrete that you would never want to make concrete countertops out of. It has a different purpose. It runs on a different time scale. So that's another thing to keep in mind is we work on a different time scale. Our needs are different from the construction industry, so we just can't simply pick and choose arbitrarily. And of course, all these, again, are as a cement replacement, not as an addition. Finally, I'm going to wrap up the discussion of admixtures to talk about all the other ones that don't affect workability, or aren't used to change workability or strength gain. And these include pigments and polymers and fibers and defoamers and things like that. There are lots more. I counted 27 different recognized superplasticizer types in the design and control of concrete mixtures. I'm only touching on the ones that are relevant to us. There are corrosion inhibitors and certainly shrinkage-reducing admixtures and things like that that I'm not even going to cover. You may want to use them, but just be aware that those are the special spices you don't need to use all the time. I'm trying to focus on the ones you're going to use all the time, that really are the core to make extraordinary concrete, as I mentioned earlier. That's what we need. That's what our customers want. So perhaps the most flamboyant admixture are your pigments. Whether they're liquids or powders, they're admixtures, and they're dosed the same way. Their job is to change the color of the cement paste to look the way you want. And as I mentioned, there are dry powders, liquid suspensions, there are natural pigments, there are synthetic iron oxide pigments, there are synthetic organic pigments that are used. Often those are the bright colors. All these are classified as pigments. There's standards they have to meet. Certainly they have to be compatible with Portland cement. I'll share a very brief story with you. Probably within the first few months of me getting started way back in the dark ages in 1999, a gentleman from New York wanted my help making a concrete countertop for himself. And that's kind of how a lot of people were in the early days contacting me before I started teaching people. And so I helped him back and forth. And as thanks, he said, hey, I own a company. We make paint, and I'm going to send you 50 pounds of ultramarine pigment. Now this is back in the day when the only blue pigment you could get was cobalt blue pigment. It was very, very expensive. Cobalt oxide is a toxic metal, and cobalt is a toxic metal. You don't really want to be exposed to it. And the blue is not very bright. It's kind of like a washed out sky blue. So that was the only way to make blue concrete. And here I had 50 pounds of the brightest, most intense blue pigment I had ever seen. It almost seemed like I could shut the lights off and it would still glow blue. So I was thrilled. I mean, this was amazing. So I made some samples with it, got all excited, and I made a small little side table just to kind of put in my showroom at the time. And I cast it. It was this brilliant ultramarine blue, gorgeous. I came into the shop the next day, pulled the forms off, and half the blue was gone. Some of it was gray, some of it was sort of a bluish gray, but none of it was the intense blue. And that's because the pigment was not stable in the alkaline environment of Portland cement-based concrete. Your pigments, if they are not stable, they will not be the color you expect them to be now or 10 years from now. They should be UV stable so you can use them outside. There's a very, very big myth that carbon black pigment fades. Carbon is a base element. Its melting point is 6,000 degrees Fahrenheit. It does not fade in the sunlight. What happens is carbon black doesn't bond well to cement, and it tends to wash out of your concrete. Whenever you're using pigments, whether it's liquid or powder, never exceed a maximum dosage of 10% with Portland cement-based concrete, because the more pigment you add, the more you're weakening your cement paste. Liquids they're basically powdered pigments in a liquid suspension. So there's a liquid with a suspending agent, and they add a powder to it, blend it together. Just like latex paint, you go to the hardware store, you buy a can of paint, you have to stir it. Liquid pigments probably have to stir them. There's suspension. I treat them the same way. So when I'm formulating colors, I still weigh out 10 grams of liquid pigment just like I would add 10 grams of dry pigment, but they may look different. But I treat them the same way. Some pigments are heat sensitive. Synthetic yellows tend to be the most sensitive to heat. So I've never seen it, but apparently if you spill boiling water on some synthetic yellows, it could actually cause it to fade or change color. Carbon black has the highest heat stability. The house is going to burn down long before carbon black is going to change color. Dry pigments, because they're dry, they tend to streak and clump if they're not mixed properly. The best way to get around this is you put them in your mixer right up front, right along with the rocks, and add your super plasticizer right along with them, and just basically wet blend your water, your aggregates, your pigment, and super plasticizer for a couple minutes before you ever add anything else. And that takes care of the streaks. Adding pigments at the end is almost guarantees streaks. Liquid pigments disperse better because of the dispersing agent, but I've seen them have a retarding effect where they slow the strength gain down, and I'm not thrilled by that. Sometimes you don't have a choice. I've also seen some synthetic pigments, especially some of the really bright, pure colors, can have a plasticizing effect. So when you're making your samples, you have to be aware that you may not be able to use your super plasticizer with these particular colors, because all of a sudden, if you did, you'd have soup. And of course, anytime you add a lot of a pigment, you're adding a lot of a fine particle that has a lot of surface area, you're going to be changing the workability of your concrete. This is most prevalent with carbon black, which is very, very small particles. High doses of carbon black can really affect the workability, make it difficult to make it flowable or pourable. I had mentioned that I dose them the same way, liquids and dries. Always add your pigments to your mixer. Never add to the mix water. This is a context thing. If you have a bucket of mixed water that's carefully weighed out, it's exactly the amount of water you need, and you add your pigments to the water, the pigments are going to settle to the bottom of the bucket. Even if you stir it, there's still going to be some pigment in the bottom, because it's not like you're adding grape Kool-Aid to the water and it dissolves. The pigments are still particles. When you dump that colored water into your mixer, most of your pigment's still going to be in the bottom of the bucket. Now, how do you get it out? Why did you do that in the first place? Put it in your mixer. The job of a mixer is to mix. That idea of adding pigment to the water comes from making bagged concrete products, say like concrete overlays that are tinted. You always have a bucket of your water and probably polymer in it, and then you add the bagged mix to that. Well, the rule of adding pigments to the water before you add your mix makes sense, but only if you start with your water and then you add your your dry ingredients to that water slowly in that specific event. But if you're making from scratch mix, add your dry pigments with your sand and your rocks up front. They're going to disperse better. And I already mentioned the carbon black, so I'm not going to repeat it. Another admixture that's used, it's certainly a critical, important ingredient in GFRC, but it's used a lot in all forms of concrete, is polymer. And polymer is added to your concrete for a variety of different reasons. When it's added to the concrete as an admixture, it's used to increase your flexural or bending strength. It can have some effect on tensile strength, but not a lot. It's mainly used to decrease porosity, to help hold in internal water so the concrete cures more evenly. And because the polymer does tend to, it doesn't make the mixed water thicker, but it can help reduce bleeding because it can help make the concrete more consistent. It tends to be a workability aid without being it's not a super plasticizer, but it can help your mix move around a lot better. So you don't need to add extra water. The effects of the polymer depends on the type of the polymer, the chemistry, and how much you use. And when you dose polymer, it's dosed based on the polymer solids to cement ratio. So liquid polymer, there's a certain amount of it that's actually solid, and that's the part that matters, and the rest of it's a liquid that counts as your mixed water. So it's just like you're dosing your pigments, you dose polymers the same way, or dose any admixture. It's the solids content to cement weight. Most polymers are described as latex. Latex simply means it's a water-based emulsion. There are natural rubbers that are real latex. They come from latex trees. We don't use those too much because they're UV sensitive, and we tend to use synthetic ones. And there's a whole bunch of different types. The main three are the styrene butadiene rubbers, SBRs, the ethylene vinyl acetates, the EVAs, and then the polyacrylic esters, the PAEs, or they typically are known as acrylics. There are also polyvinyl acetates and some other ones too. There are epoxies too that can be blended into concrete. The ones we like to use are the acrylics. Certainly GFRC uses an acrylic. In the decorative concrete world, the most common ones are used for overlays, whether it's skim coats or stampable overlays or things like that. These are glues. They're bonding agents. They can be added to the mix, but they're mainly rolled on or brushed on or troweled on to act as a bonding agent, a glue, in other words. Sometimes they're also blended into the mix to give it a better flexural property so that the thin overlay doesn't crack as much. And they tend to have high solids contents. GFRC does use a specialized acrylic latex polymer. The main reason it's used is for moisture retention as a curing aid, so that when you're making your GFRC out of Portland cement, because the concrete's very thin, it would normally have a tendency to dry out very quickly. But the polymer helps to retain the moisture so that it achieves a sufficiently high 7-day strength that's basically equivalent to curing that piece of GFRC in a moist environment for 7 days. So it's a curing aid. Its secondary benefits are also very important. It gives the mix a stickiness. When you're spraying GFRC, the part you spray is called a mist coat. That's the part you see. And trying to spray a mist coat that doesn't have polymer on a waxed mold is almost impossible. So the polymer helps it stick. It's an essential ingredient to making the whole idea of spraying your concrete work. If you don't have it, your mist coat just runs and slides, and it's just awful to work with. So it's a secondary benefit. It's almost like it's an afterthought, but it's an important afterthought that it makes the mist coat stick. The GFRC polymers, it's called a non-rewettable polymer, which means that once it dries, it stays stretchy and flexible, but if you get it wet again, it doesn't turn back into a liquid. which means GFRC polymers cannot be turned into a powder. You can't use a powdered polymer as a GFRC polymer because they don't work that way. And to get that, I mentioned the 7-day wet cure strength, it takes a certain amount of polymer, and that minimum polymer solids content is 5%, but most of the industry uses 6%. Again, that's 6 pounds of polymer solids for every 100 pounds of cement. The polymer of choice in the industry is Forton. It's been used for probably the last 30 or 40 years worldwide. Has a very, very broad and long track record, very good success rate. Has a lot of specialty additives, defoamers, wetting agents in it that basically have tuned a generic polymer to be a high performance polymer for GFRC to give a very high surface quality. There are other GFRC polymers on the market. The other industry polymer that's used for GFRC is called Polyplex. It's a different brand, functions the same way, it's used the same way. Some people prefer it, some people prefer Forton. It's kind of like, what brand of ketchup do you like? There are some powdered polymers on the market that are being used in GFRC that I believe are risky. There's no test data on it. The dose that's suggested is half the recommended dose that is necessary, that many tests have shown to get that 7-day strength. You have to have 5 to 6%. If you only use 3%, you're not getting that. So your concrete's drying out and losing strength faster. I think the only reason why a 3% is being suggested is so that it looks more cost effective, which is a very short-sighted approach that is very irresponsible of the manufacturer. And until they provide test data, it's one I definitely would tell people to shy away from. When you make GFRC, it's a very specialized form of concrete that depends on it being made right with the right ingredients. And that's the only way to extract the high flexural strength to be able to make very thin concrete that's resilient, crack resistant, and because it's thin, it's light. That's a very well understood industry that's been used globally for 40 years. The ingredients and all that are very, very well categorized and tested and understood. There are actually specs, international specs for it. And these all say 5 to 6 to 7% polymer solids for wet cure. If you choose to use something else and use less polymer, you're going to have to wet cure your concrete for the full 7 days to get that 7-day wet strength, which is like, that's why you use polymer in the first place, is so you don't have to do that. And again, I'm being a little critical, but there are some new products coming on the market that don't have any test data. Just because somebody who sells it says it's good, you shouldn't believe them. Show me the test data. That's my role, is to be sort of an industry watchdog, to look out for you guys. Be careful. Just because somebody sells it doesn't mean it's good. So I had mentioned before that different polymers have different amounts. Some of it's polymer solids, some of it is the liquid, and this is sort of a schematic diagram I drew that illustrates that. Forton is a 51% solids. A very popular bonding agent, Acryl 60, which you brush on a existing layer of concrete and you're going to put another layer of concrete over it. It's sort of like a glue in between. It's a 28% solids. So with Forton, about a little more than half of it is polymer solids, and a little less than half of it is equivalent to the water. Well, when you use polymer in your mix design, that water that's part of the polymer counts as part of your mix water. So you can kind of see how the math will get a little bit challenging to do on your own. I already mentioned all that, so I'm not going to read it again. Fortunately, I hate to sound like a salesman, but my GFRZ mix calculator does all that for you. So you can input Forton, which is a 47%. You can input Forton, which is 51% solids, Polyplex 47% solids, and you can change the polymer solids load, the target amount 6%, 7%. If I'm going to do something really thin, that I want it to have a more flexibility to it. Let's say I'm doing a really long backsplash and I was doing it quite thin, like 1 centimeter thick, and I don't want it to crack, I might up the polymer solids content to say 10 or 12%. You can do that. The calculator does all the math for you and deals with the water, et cetera, et cetera. So it deals with all the messy bits of having to work with the liquid without having to be burdened with all the math and getting things wrong. Now, I had mentioned that Forton has other specialty admixtures added to it to improve its properties, and one of those is a defoaming agent. Now, there are a few commercial defoaming agents on the market. They're generally sold as powders to be used in like self-leveling overlay mixes, where you're basically pouring on a thin layer of concrete that sort of self-levels on its own, and you don't want bubbles in it. Bubbles, defoaming agents help break up the foam that's generated as you mix concrete. And there are many different ingredients that can cause foaming. Some superplasticizers can cause foaming. There can be foaming from your pigments, can be foaming from just general ingredients. And defoamers don't make they don't make the air go away. What they do is they help break up the air bubbles so that instead of having a stable foam, like when you shampoo your hair in the morning in the shower, you can grab a handful of that foam and you can mash it around, and the foam's very stable. The bubbles don't break up easily. But the defoamers do. They break all the surface tension, so the foam, the bubbles basically they burst, and the air that's trapped inside the bubble can coalesce into bigger bubbles and then move out of the concrete. So defoamers are most effective when you're trying to make very, very flowable, pourable concrete, when you're trying to vibrate the concrete or making SCC. They have almost no effect when your concrete is so stiff that air bubbles are stuck. Because, again, defoamers don't make the air disappear. They just make the foam unstable so that the air that's inside the bubble can rise out on its own. I don't have a particular brand that I could recommend. People have used a little tiny bit of isopropyl alcohol, rubbing alcohol, a teaspoon or two. Some folks have used a chemical called tributyl phosphate. It can be kind of nasty, and it's not cheap. But again, you only have to use a tiny bit. Often, the way they're used is you'll have your you could have your bucket of mixed water, and you just add a little bit, a few milliliters, to the mix, and it tends to look like oil, so it sort of floats on the surface. And then when you add it to your mix, it helps prevent the foam from forming. Or if you add them at the tail end of mixing, you can actually watch the bubbles burst, the foam at the surface burst. Either way is fine, but generally, if I put them up front, there's less air that stays in the concrete. I tend to try to use as little as possible because we don't really know what the effect on the concrete is. We're using so little, it's doubtful that it has any real effect on the concrete. And if you're going to be using air-entrained concrete, which I'll talk about in a minute, don't use a defoamer, because the purpose of air-entraining is to put bubbles and foam in the concrete. So they kind of work at odds to each other. Normally, for interior concrete, we never ever have to use an air entrainer. And in warm climates where you don't get freezing temperatures, you don't have to use an air entrainer for outdoor concrete. Where you do is when you have a lot of freezing and thawing, whether that's one time, it gets cold in the beginning of winter and then it doesn't thaw till spring, or in the case where we are here in North Carolina, we get freezing and thawing a lot, where it might be cold and then next week it might warm up, and so we get a lot of freeze-thaw cycles. When concrete's outside, it gets rained on, it absorbs water, there's voids in the concrete, and the concrete holds a certain amount of moisture. When a concrete freezes, when it gets cold enough to freeze, that water turns into ice, and ice is less dense than water because it expands. Water expands as it freezes. If there's no place for that water to go, that ice can act like little jackhammers and gradually break up the concrete. What air entrainers do is they create billions and billions, to paraphrase Carl Sagan, of very fine microscopic bubbles. Some of them are too small to see. In this photo, it's kind of hard to see, but that aggregate particle is sort of yellowish tan. There's a 1 millimeter, there's a white line that says 1 millimeter. That's the scale of the bubbles. Now, the big bubbles that are, say, 1 millimeter in size aren't as effective as the tiny ones that are 10th or 100th of a millimeter. And those are the ones that are considered entrained air. And they act like a pressure relief, so that as the freezing water expands, doesn't all, I mean, as water freezes and expands, it doesn't all happen all instantaneously. These empty bubbles act like a reservoir or pressure relief to let the water move into. So as the ice expands and pushes away the liquid water, that liquid water has a place to go. And when the concrete thaws, the air pressure that's inside that little bubble pushes the water back out. So there are little pressure relief chambers like shock absorbers. Typically, the amount of air that you're targeting is 4 to 6%, sometimes a little bit higher than that, but generally 4 to 6%. So that's the total volume. So if you had a cubic meter of concrete, 6% of that cubic meter would be air, entrained air. If you're just making interior concrete and you're not doing entrained air, you're probably going to have about 3% trapped air, which is the big bubbles you tend to see that we deal with as pinholes, that are not effective as freeze-thaw resistance. So air entrainers are basically, they create microfoam inside your concrete. The benefit of doing that gives, because the air bubbles are tiny and they're sort of spherical, they do act like little foamy, spongy ball bearings. Gives the concrete workability. Also gives it some stickiness, which tend to help keep the concrete more consistent. You get less bleeding, less segregation with air entrained concrete. So for those of you folks listening who do use concrete, who do use concrete that has been air entrained, you may recognize some of these characteristics of it being sticky and has less segregation and bleeding. There is a penalty. You do lose some strength with air entrained concrete. Perhaps at 5% air entrained content, you might lose 10 to 25% of your compressive strength because of that. Now that sounds pretty extreme, but if we're already making super strong concrete, we can afford to lose that and not have any downsides. I suspect that it's more likely on the low end, not the high end. I wouldn't worry about it too much, but air entrained concrete always is a little bit weaker than non-air entrained concrete. Again, this is a summary. Only when your concrete's subjected to freezing and thawing. Interior concrete, don't worry about it because I doubt your clients are going to let their house freeze. Thing to keep in mind, and the reason I put this in is I just had a student of mine ask me, he's putting in a big outdoor table and it's going into 10 degree weather, 10 degree Fahrenheit weather. So that's minus something, minus cold centigrade. The concrete still needs to be strong enough. So 4,500 psi that's 1 or 2 days with my mixes, so that's no big deal. Water cement ratio below 0.45, we got that because we never go that high. Wet cured for at least 7 days, that's to give it enough time to gain strength and for the cement to start consuming some of that mix water, because we don't want a lot of excess water in the mix to freeze to turn into ice. So the lower the water cement ratio and the longer it's cured, the less excess water there is to turn into ice and to cause problems. And then they want that concrete to dry out, basically to get the excess water out of the concrete, in this case 30 days, but I suspect they're talking about slabs on grade, let's say. So I would maybe say a few days at most. It may not even be necessary if you seal the concrete. Now, fibers are technically not admixtures, but because we do add them to the concrete to improve the concrete, and because they're used so widely, and there's a lot of misunderstanding about them, I felt it's important to talk about them. The reason we use them, concrete countertop people use them, that is we want to boost our flexural or bending strength. We're going to get a little bit better tensile strength because of it. Depending on the fiber, we can get better chip resistance, that's called toughness, and fracture resistance. That doesn't mean it's going to be chip proof. It doesn't mean we can make pretzels out of our concrete. But what you see there in the photos of flexural tests I did on some concrete, that's 5/8 of an inch thick, 16 millimeters over a span of 10.5 inches. Don't know what that is in metric. 260 something millimeters. It's bending quite a bit with no visible cracks. That's what fibers can do for you. Fibers do not replace structural reinforcement. So if you're making conventional concrete that requires steel, you're making a bridge girder, for instance, you can add fibers to it to reduce cracking, but it's not going to replace the steel. Now, GFRC does use fibers as a structural reinforcement, but we're using about 100 times more fibers than is used in conventional concrete. So, and they're different kinds of fibers. So when you use fibers, you're always going to get good crack control and some other benefits when you're dealing with the fresh concrete. But not all fibers give you hardened concrete benefits. Those tend to be called, they're structural fibers, and I'm going to get into those in a minute. Most of the time, for what most of the construction industry uses fibers for is for plastic shrinkage control or secondary reinforcement, not structural or primary reinforcement. And the way the fibers work is that the fibers act like a three-dimensional net that helps suspend and hold the rocks and the sand in place. Because here's what we're trying to combat. If you just had an ordinary concrete mix that came out of the truck, but it had too much water in it, comes down the chute, you spread it out, bull float it, waiting for everything to happen. As it's sitting there, gravity is pulling down on everything. So gravity is causing the rocks and the sand to settle. Big rocks settle faster than small rocks. That's Stokes' law, by the way. Big rocks settle faster, and as they do, they squeeze out. All the fine sand acts like a filter, just like a pool filter uses sand to filter out the dirt in the pool water and the algae and whatnot. The big rocks squeeze everything together. The sand surrounding that acts as a filter, and the mixed water is squeezed out, and it forces its way out in all directions, and there are only two directions for it to go. The shortest paths are up toward the surface and down toward the subgrade. In order for it to get there, the more it's squeezed and the more water that has to come out, the bigger the channels it has to form. And those channels don't go away. So those channels form weak spots that can turn into cracks. These big open channels make the concrete very porous. You have trapped water pockets under the rocks that can create voids that can lead to spalling and pop-outs. That bleed water on the surface can alter the water-cement ratio of the surface if that isn't removed or allowed to dry before finishing begins. So a whole host of problems of trying to work on concrete that has too much mixed water in it and working on trying to finish concrete that has bleed water on it leads to all the problems that are solved by mixing fibers into the concrete. And what the fibers do is they keep the rocks from settling. And if you stop the rocks from settling, you stop the whole chain of events that leads to bleed water happening. That's why fibers are used in ordinary concrete. It has nothing to do with the hardened strength properties of the concrete. all they do is they keep the concrete from going bad. They don't actually make it better. There are a whole bunch of different fibers, and I'm going to touch on a few of them. Most of these are for secondary reinforcement. These include polypropylene, polyolefin, cellulose, natural fibers, nylon, and all that. These materials just don't have the strength, and what's more important, they're too stretchy to be effective as little bars of rebar. It's a very approximate way of thinking of fibers, structural fibers. These are meant to stabilize the mix, to give it good properties so you don't get the bleed water, so you get better concrete, or you don't let your concrete go bad. Structural fibers, on the other hand, that do provide true tensile reinforcement, and that's why GFRC uses an alkaline-resistant glass fiber. It's a structural fiber, very high tensile strength, very, very stiff, not stretchy at all. Carbon fibers are the stiffest. It's called the modulus of the fiber. Steel has a modulus of about 30 million psi. Carbon fiber can be 2 to 3 or 10 times that. Glass is about 1/3 of this. Glass is about 3 times stretchier than steel, but it's still very, very stiff relative to the cement that it's encapsulated in, that encapsulates the fibers, I should say. So structural fibers are both strong and very stiff. Kevlar is very stiff, very strong. PVA fibers are very stiff, very strong. All these have these characteristics. What is different is the size and the appearance of them and how well they bond to the concrete. Of course, the cost is a big factor. Carbon fibers are very expensive, and they're black, so they'll show. And steel fibers are very strong. They're not that expensive, but they're ugly, and some of them are quite big. The ones we use are glass fibers and the PVA fibers. PVA fibers are really cool because they're synthetic fibers that are finer than a human hair, or the ones we tend to use. And the cement paste bonds to them really well. They're used for microcrack control. Because they're so fine, it's easy to overdose them, and when you start to use too many PVA fibers, you can actually end up with concrete that's weaker than the concrete would have been if you hadn't used PVA fibers. So it's very important to use the right amount of dose. It's easy to overdose them. And they can lead to hairy surfaces, hairy concrete, because they can stick up a little bit, although a blowtorch or just sanding them off makes it go away very easily. Glass fibers, on the other hand, are much bigger. You always see glass fibers. The big 19 millimeter ones used for GFRC are quite visible. You can't burn them off because it's glass. But they don't stick out. They will polish beautifully, so you can polish them so you don't feel them at all. And then Kevlar's an exotic fiber that we never use. The yellow fibers, and these are some of the factors of why you would use one fiber over the other. I've touched on them. The second and third points on this list are important. Short fibers are less effective than long fibers. Thick long fibers are strong, true, but there's not a whole lot of surface area relative to that fiber than, say, short, very small diameter fibers. It's called the aspect ratio, the length to diameter ratio. So when you buy fibers, the fiber manufacturers have tailored the length to diameter ratios for you. You don't have to think about that. All you have to do is look at lengths. The longer the fiber, the better it's going to be, because most fibers fail from pullout, where the fiber physically just pulls out of the concrete. It's pretty rare to actually see fibers failing, at least early on. Long term, that's a possibility, but generally your short-term failure is fiber pullout. So your longer fibers are going to give you better early green strengths than long term. That's why GFRC uses, or I think I always use 19 millimeter fibers, not the shorter 13 millimeter fibers, because they're longer. They're 50% longer. They have a much higher pullout resistance, and of course, higher doses give you more strength, provided you're not trapping. Fibers have a lot of surface area, and if you add too many fibers, you start trapping a lot of air in the mix, and air doesn't have any strength, and air displaces your cement paste. So you actually can make very fluffy, lightweight, foamy fibrous concrete that isn't very strong because you added too many fibers to it. So it's very careful not to use too many fibers. With GFRC, I'm going to touch on it in a minute, but it's important to use a certain amount to get the kind of properties. Otherwise, you're just dealing with brittle, a brittle non-aggregate based mortar mix if you don't have enough fibers in it. So when you put mixed fibers into your concrete, let's say you're making wet cast concrete, you add your fibers in, it's mixing, and then you pour it into your mold. Your fibers are oriented in a 3D orientation where the fibers are just randomly poking in all different directions. With GFRC, the backer that's mixed, and I'll show you a picture of what that looks like in a minute, is laid in a thin layer and then compacted with a special roller. And that roller, what it does is it lays the fibers down and flattens them out so that they kind of lay in a flat plane, kind of like OSB, or oriented strand fiber board. 3D orientation, about 5 to 10% of those fibers are actually pointing in the direction that do any good. The rest of them are pointing in other directions that aren't resisting the direction tensile load that you have to be interested in. With 2D orientation, that goes up to about, at the low end 33%, up the high end about 50%. So you get a much more efficient use of those fibers for the same amount of fibers. That's why compaction is so critically important in GFRC, and that's why I am a strong advocate against making lazy SCC GFRC where you just mix it and pour it and walk away, because you're only getting 3D orientation. Yes, you have the fibers in there, but only a fraction of what you expect are actually doing any work. So you're shortchanging yourself. You're making relatively weak but very expensive concrete, and that's not what we want to do. Make it right and you'll get strong concrete. So the fibers in GFRC, because GFRC depends on fibers, it uses an alkaline resistant glass fiber so the glass doesn't break down from the alkalinity. These come in two different lengths, 13 and 19 millimeter. You certainly can make decent GFRC with 13 millimeter, but you're always going to be making stronger concrete with 19 millimeter fibers, which is a preference of mine to make good strong concrete. That lets me make thinner concrete with more confidence. Early on I talked about how admixtures were dosed, how you had the dry weight of admixture added to 100 weight of dry cement binder, pound for pound, kilo for kilo. Fibers are not dosed that way. They're not dosed that way. The way they're done is kind of confusing. It's a little bizarre, but that's how the industry does it. It's called a volume fraction. And what's misleading is it has nothing to do with volume. It's all done by weight. The way fibers are dosed is a 3% dose is 3 kilos of fibers added to 97 kilos of concrete to make 100 kilos of fiber reinforced concrete. That's how it's done. So that when I mean concrete, I mean your aggregates, your pigments, other admixtures, your water, polymer, cement, pozzolan, you name it. Everything that goes in the concrete counts as concrete. So it can be a little confusing, but that's how it's done. So GFRC, to get the kind of flexural strength and to get the kind of properties that you expect when you make it, you have to use at least a 3% dose. I've done a 4% dose as well. It's kind of hard to work with 5%. So 3% is your typical, that's the effective dose, and that's the one I recommend for a lot of people. And what you're seeing in the bottom on the left are 19 millimeter fibers. That's a 3% dose being mixed into the GFRC. The mist coat is the material. It's everything but the fibers. When you mix the fibers into it, it turns into the structural backer that is GFRC. So the left picture is what it looks like before it's mixed. The right picture is what it looks like after it's mixed. That's a 3% dose. That's a lot of fibers. But that's what it takes to make strong concrete that has a high flexural strength. So to kind of wrap things up and summarize, I'm going to give you some recommended admixtures, which I think everybody should use. They're going to let you make very good concrete, get the kind of appearance that you want, tight surface finish, few bug holes, maybe no bug holes at all, easy to work with, lots of set time, or lots of work time, I should say. Good short-term, great long-term strength. So for precast concrete, the Rytec Super Plasticizer, polycarboxylate, paired with a viscosity modifier, you can use ice by itself, or if you want to get more work time, you can use a little bit of citric acid. If you're going to dabble with CSA cements, the Rapid Set cement, you need to use citric acid. It's the only retarder that is effective with it. And it also happens to boost your strength. So you get super, super strong concrete the very next day after you cast it. The pozzolan, if you're going to use Portland cement, I would recommend VCAS. Metakaolin's a good alternative, but it will reduce your workability. So that's why a lot of folks prefer VCAS. Some of my mix designs don't use fibers. You can always add fibers to any mix design. You're going to have to vary the dose as needed. Of the PVA fibers, I recommend the Nikon Rec 15s. They're 8 millimeters long, so a little more than a 1/4 inch long, but they're, like I said, finer than a human hair, and when they're properly dispersed, you cannot see them. And if you wanted to use a much less expensive fiber, the NEG 1/2 inch or 13 millimeter AR glass fibers, you can mix those in, but they will show. You can go to my store. I sell products. Go to my store, you can see these ingredients, or you can get them elsewhere. If you're making GFRC, you certainly have to have glass fibers, and I'd strongly recommend the 19 millimeter fibers. You have to have a polymer. Again, mainly for curing, but also for the flexibility, the crack resistance, the stickiness to get it to stick to the forms. That's why I still use it with CSA cements. It reduces the brittleness of the concrete, giving the GFRC the more flexibility it needs to get that strength, that bending strength. So the polymers are critically important, fibers are critically important, and the rest of it is the same as precast. So that wraps up the summary of all these admixtures. There are others that I haven't covered, but I don't think you really need to dabble in them. Certainly you can Google and find other sources that if you were interested in using some of these more esoteric admixtures, you can find out how to deal with them. But by and large, these are the admixtures you need. You don't need a lot of other complex admixtures. Keep it simple, keep it straightforward, keep it easy to manage. Use reliable ingredients that are trusted and tested, and you're going to be making good concrete, and you're not going to have to worry about your concrete going south on you. Now, I'll answer questions. Go ahead and start typing them in. I know some folks have been already typing some in, and I've been answering them as I go, but certainly you might be waiting. Go ahead and type them in. I'm going to take as much time as I need to answer all of your questions because your input's important to me. And while you're doing that, Lane's going to explain a special offer we have for you. So with that, I'm going to hand my headset over to her and start typing in your questions for me.
Thanks, Jeff, and thanks everybody for hanging in there with us. I hope that this was super informative for you. You can see here on this next slide that we have a super Christmas sale on Precast Mix Design 101. It's a self-study course. This is a self-study course that really builds on what you learned today. As Jeff mentioned at the beginning, this builds on understanding the primary ingredients in concrete, the secondary ingredients like the admixtures that he's explained today, and it also adds a lot more detail, including actual mix formulas. So what it consists of, there's a textbook that serves as a reference manual, and it's really handy because you can look up a lot of the things that Jeff talked about today without having to fast forward through the recording of the seminar. Sometimes it's a little bit hard. It's great to watch a video, but then sometimes it's a little bit hard to use that as a reference. So the textbook is a great reference. The textbook also includes more than what was covered in this seminar. It tells you exactly how to mix, for example, what order to add the ingredients to the mixer step by step, how long to mix them, which is really important. It also includes mixed troubleshooting such as air bubble, segregation, things like that. And it also includes a grout formula, which is also known as slurry. Plus, and this is a huge plus, besides having the actual mix formulas in there for a couple of precast mixes, it has a mix calculator that takes all of the math out of this. We had some questions about percentages and calculating these percentages. With the mix calculator, you don't have to do any of that math. You just plug in the square footage or square meters, the thickness that you're making, and it prints out a batch report with the exact weights to use of every ingredient. The mix calculator also includes that ice calculator that Jeff was mentioned, so you don't have to guess on your ice. This course, I guarantee that it will help you. But if for any reason you don't like it, we'll refund your money, no questions asked, so there's absolutely no risk. And we want you guys to be successful at concrete mixes. So as part of our Christmas sale, Precast Mix Design 101 is half price right now, making it just $49.50 until December 31st. And you've all shown that you're really studious, you're serious by sticking with us here today. So I think you'll really enjoy further in-depth learning about precast concrete mixes as well as the actual concrete mix designs. So to order this, I've prepared a little convenient link for you. You simply type in the text you see here in your browser, the orange text, bit.ly/mixdesign, MIXDESIGN 2013, exactly like that. Type it into your browser like Internet Explorer or Firefox or whatever web browser you use. Right now while you're sitting at your computer, it automatically brings up the shopping cart with the self-study already in it at the reduced price. And then all you need to do is enter your credit card information. Once you do that, you'll be able to access the self-study instantly via a link that you receive in your email inbox. And by the way, a lot of our most popular self-studies are half price as well, so you may want to click on Continue Shopping and look at some of the other ones. So as a summary, this self-study course contains actual mix formulas so that you can actually make that extraordinary concrete using the admixtures that you learned about today. So again, just type in bit.ly/mixdesign2013 into your browser and you'll see the shopping cart. Okay, so that's our special offer. It seems to make a lot of sense based on the foundation that you learned in this seminar, so I wanted to present it to you today. All right, so we're going to take some questions now. We've got several, and I'm going to hand the headset back to Jeff.
We got a big list of questions, and Lane's got to organize it for me. So some of these I've already answered, and she's kind of culled those, and then there's a bunch that I haven't done. Wow, that's a big list. So here we go. We're going to start at the top. Okay. Do you know if Vitro Minerals is distributed in Canada? Call them. I don't know. Probably. We ship. I know we ship it because we sell it.
Probably anybody who sells it.
Okay, Jim, you asked, do you need to compact if a backer is sprayed on? Absolutely, always. A sprayer is merely a way to get the backer on evenly. You always have to compact the backer. And if you do spray it, you can see it's kind of fluffy. Very important to compact. Do you recommend a power blanket as a heat source for curing in a colder environment? Do they tend to heat slowly enough to encourage good curing? Power blankets are big, expensive electric blankets designed for outdoor concrete work in very cold temperatures. So yes, they are designed to heat slowly. Do I recommend them? I think they're a big waste of money. They're $700, hundreds of dollars a piece. I think it's kind of silly to spend that kind of money. Some people think it's important. I've never ever had to do that. If you use warm water to get your concrete up to warm temperatures, let's say if you're talking in Fahrenheit, you get your concrete up to 60 or 65 degrees. So that's what, 15, 18 degrees centigrade. Your reaction rate is going to be more normal. Cast your concrete, cover your concrete in plastic like you normally would, and then go to a thrift shop and get some old tarps and blankets and quilts, or get some insulation and cover your concrete. Okay, so it's going to make its own heat. You just need to trap it. It's not going to be as effective, but it's going to be a whole lot cheaper. What some people have done is they've gone to Walmart or Target or some sort of home store and bought a regular electric heating blanket you put on your bed. Put that on top of the plastic. I like to double layer the plastic, and then cover that with insulation. You're just trying to get the concrete to be warm, 80 degrees Fahrenheit, which is what, 27 C, something like that. Not hot, just warm enough to cure at a normal rate. That's going to do it. Some people have built little tents and put just electric heaters underneath their casting tables. That works too. So the big power blankets are designed to make the concrete really hot for some specialized reasons. They're not necessary. Next question. Do you recommend using 20% of pure CSA as a replacement? No, I don't. Will that achieve a strength advantage? It might, but it just makes your concrete really complicated. It's going to make your concrete set really fast, and you may not be able to deal with it. Does the face coat and backer coat have to be dosed at the same rate? If it's pigment, no. If it's superplasticizer, no. If it's polymer, yes. If it's fiber, well, no, because the face coat doesn't have glass fibers in it. Doesn't seem that. So Brett, you've asked a couple questions. I'm using a white silica fume in my mix, so it's going to reduce your workability a lot and make it sticky. What do you think it is? Do you think it is detrimental since it is white? No, if you know how to manage it, or if you physically know how to deal with it with superplasticizers. It's white because it doesn't have the irons in it that regular does. It has zirconia in it. That's what makes it expensive. I don't know enough about your mix design to help you any more than silica fume is going to give you very different work properties than VCAS or metakaolin. With my mix design, if you may want to try less. If you're using like a 5 or 10% silica fume, that's about as much as you should go. If you're an Ultimate student, which I believe you are, just give me a call because you have my phone number. We can talk privately. Robert, let's see, I believe in the slide before the sugar retarder slide, one of the points about retarder states early strength is reduced. So if you're if you're using a retarder to slow down your set time, you're probably also reducing your early strength, which means you need to leave your pieces sit in the forms perhaps a day or two longer. Do I have customers in Scandinavia? I have a student in Finland, but he doesn't sell products. He makes concrete. We might be able to help you. We certainly ship all over the world. That may not be economically cost-effective, but we'll follow up with your tour. I don't currently use pozzolans. Do the properties help minimize curling during the curing process? Yes. Or could it be the combination of water reducer and the accelerator I use? Don't know. It's too hard to describe and diagnose from just a general statement. You're probably not using enough water reducer and probably using too much water. So curling is generally caused by differential drying where one side dries faster than the other, and that's largely driven by water content in the concrete and permeability or porosity of the concrete as it's drying out. So there's many, many different factors that could be leading to that. Looks like air entrained concrete has a different surface appearance. Could it be used interior if you like it? Sure, why not? Do small bubbles cause issues with staining dirt? Well, you'd probably be grouting your concrete or sealing it, so it's just like any other concrete. Maybe. People have to keep their concrete clean, right? But the micro bubbles from air entrained concrete are very, very small, very difficult to grout. You may have to use a densifier or even a topical coating to deal with that. Okay, lots of bubbles on the finished surface make a cream finish more difficult to attain. That's true.
Yeah, so if you do air and trained, I would say don't offer.
So if you do air and trained concrete, I probably wouldn't do a cream finish, or you'd have to do a lot of grouting and just set the expectation that your surface isn't going to be Formica smooth. Oh, well, Merry Christmas, Brian. He's left. What's the best way to get pure white concrete using 100% CSA cement? Excellent question. I would recommend using a very high loading of titanium white. Because CSA cements react so fast and you get stupid strong concrete, you can exceed the 10% limit. So what if you lose a quarter of your strength? You're still making very, very strong concrete. Try a 15% loading and see what that gives you. I've done it and it's worked. I've made pretty white concrete. If you had to make white concrete and you didn't want to go that route, I would use white Portland cement with titanium white pigment, possibly use an accelerator, a chemical accelerator, chill the concrete with ice to give you work time, and then heat the concrete as it's curing. So you kick in the accelerator, getting higher strengths. It's very complicated, but that's a good way to do it. And the last question is, where would you use Class F fly ash over Class C? It's usually not a case of when you would use one or the other. Different coal sources create the two different classes of fly ash, so it's more of a question of where are you and what can you get. Class C fly ash has a higher self-alkalinity, it has a higher calcium oxide content. So it is somewhat described as semi-self-activating. Don't get excited. That doesn't mean that you can make 100% Class C fly ash concrete and have any kind of remotely high early strength at all. It just means that it has slightly different chemical composition. East Coast coal tends to be more Class F. West Coast tends to be more Class C. You're going to get whatever you're going to get, and functionally they're similar. Since we don't use fly ash that often in concrete countertops, it's not a puzzle in that I'm not familiar with I'm not well versed in the subtleties between Class F and Class C as to why I would use one versus the other. I wouldn't use either of them in concrete countertops. For ordinary concrete, if you're just looking to use fly ash in your concrete, pick one that's cheaper to buy. That's how fly ash is used. It's used as a cheap replacement for your expensive cement. That's the primary reason why it's used. So that's the answer I would give you. That's it for the questions. Thanks for sticking with me for almost 3 hours. I knew it would go at least 2. That usually goes longer. I would like to wish everybody happy holidays, Merry Christmas, Kwanzaa, Happy Hanukkah, whatever you celebrate. Happy New Year. Take care. Bye-bye.